Welcome to the quiet journey, a passage through time and space that will challenge everything you think you know about the universe. For as long as humanity has gazed up at the night sky, we've looked at the stars as distant points of light, twinkling dots that offer a glimpse into the infinite expanse of space. Some stars seem closer, others farther, but all appear to fit within a pattern that we understand: familiar constellations, familiar sizes, and familiar distances. We know that stars come in different colors, from the white hot blaze of our sun to the red hue of stars in their final stages. But what if we told you that, hidden in the vast darkness of the universe, there exists a star so massive that it completely defies our imagination? This is Stephenson 218, a star so large that if you placed it at the center of our solar system, its outer layers would extend far beyond Saturn's orbit. Its surface would engulf Mercury, Venus, Earth, Mars, Jupiter, and Saturn, leaving nothing but a void where planets once existed. To even begin to understand its scale, imagine light, something that travels at 670 million miles per hour. It would take light over 8 hours just to circle this cosmic titan once. This is no ordinary star. This is a giant in every sense of the word, and it challenges the limits of what we thought was possible in the universe. But there's more. Not only is this star unimaginably large, but its very existence calls into question everything we know about how stars form, live, and die. Stephenson 218 is not just any red supergiant. It is the largest known star in the observable universe. It burns with the energy of 440,000 suns combined, yet its final days are rapidly approaching. And when its life comes to an end, it will explode in a supernova so powerful that it will outshine an entire galaxy, leaving behind a remnant that could collapse into a black hole or a neutron star. This journey isn't just about a star. It's about understanding the very nature of the universe itself. It's about questioning the size, scale, and limits of celestial bodies. Stephenson 218 isn't just a scientific discovery. It's a moment in history that forces us to look at the cosmos with fresh eyes. And we are only beginning to comprehend its full impact. For decades, humanity was unaware of such a colossal star. In fact, it wasn't until 2012 that astronomers first uncovered Stephenson 218, hidden behind thick layers of cosmic dust, tucked away in the Scutum constellation, some 20,000 light-years from Earth. The discovery was nothing short of revolutionary. Here was a star so massive that if placed in the center of our solar system, it would stretch past the orbit of Saturn and swallow everything inside its grasp. Yet, for all its size, it remained invisible to the human eye, shrouded in the obscuring veil of interstellar dust. But how was such a star discovered? How did astronomers detect a cosmic giant that had been hidden from view for eons? The answer lies in the power of modern technology. The discovery of Stephenson 218 wasn't made by simply looking up through a telescope. It required a revolution in our ability to see beyond what is visible. The key to uncovering this stellar titan lay in infrared astronomy. Infrared telescopes, unlike their visible light counterparts, can peer through the thick clouds of dust that block the view of stars like Stephenson 218. In the same way that night vision goggles allow us to see in darkness, infrared observatories like the Gaia Space Observatory and the Spitzer Space Telescope can observe objects hidden behind cosmic curtains, revealing stars that would otherwise remain unseen. But even with the power of infrared technology, measuring the size of a star located 20,000 light-years away is no simple task. To understand the enormity of Stephenson 218, astronomers had to first find a way to measure it across vast distances. This required a combination of complex measurements, including parallax, which tracks the shift in position of a star as Earth orbits the Sun. With this data, astronomers were able to calculate the distance to Stephenson 218, and from there, determine its angular diameter, giving them the measurements that ultimately revealed its staggering size. When these measurements came back, they were nothing short of astonishing. Stephenson 218 was not just large. It was so large that it exceeded the limits of what we thought was possible. Its radius is about 2,150 times the radius of our Sun, placing it in a class of stars that are not just larger than anything we had seen before, but beyond the bounds of ordinary comprehension. In fact, it is so large that if we could somehow place it where our Sun sits in the solar system, its outer layers would extend past Saturn's orbit, leaving no room for the planets Mercury, Venus, Earth, or Mars. If Stephenson 218 were the size of a basketball, it would be as large as the Empire State Building standing on top of that basketball, 1,700 feet tall. But size alone doesn't capture the full extent of what makes Stephenson 218 so remarkable. This star isn't just big. It burns with an intensity that is nearly incomprehensible. Its brightness is equivalent to that of 440,000 suns, making it one of the most powerful sources of light and energy in the universe. Yet despite this immense luminosity, it is surprisingly cool. The surface temperature of Stephenson 218 is about 3,200 Kelvin, much cooler than the Sun's surface temperature of 5,778 Kelvin. This cool temperature, combined with its massive size, gives it its characteristic red color, a hallmark of red supergiants in the final stages of their lives. So, how did a star like Stephenson 218 form? What forces are at work to create such a massive object in the first place? The answer lies in the way stars evolve, especially the evolution of massive stars. The life cycle of a star like Stephenson 218 begins in the cold depths of space, where clouds of gas and dust slowly collapse under their own gravity, eventually forming a dense core. As the core becomes increasingly dense, nuclear fusion begins, and the star starts burning hydrogen into helium. This marks the start of a star's life. However, the evolution of massive stars differs greatly from that of smaller stars, like our Sun. While the Sun will burn hydrogen for billions of years, stars much more massive than the Sun live fast and die young. Stars like Stephenson 218 burn through their hydrogen fuel in just a few million years, causing them to rapidly expand into supergiants. During this phase, the star begins to burn heavier elements, leading to an outward expansion that results in its enormous size. As the fusion process continues, the star will eventually exhaust its hydrogen and move on to burning heavier elements like helium, carbon, oxygen, and so on, until it reaches iron, the final stage before death. But for Stephenson 218, the end is drawing near. Like all massive stars, it will eventually reach the limit of its fuel supply, and when that happens, it will begin to collapse. This collapse will trigger an explosion, a supernova, that will be one of the most violent events in the universe. The death of Stephenson 218 will release more energy than our Sun will emit in its entire lifetime. When this star explodes, it will briefly outshine an entire galaxy, providing a fleeting glimpse into the power and chaos that can unfold when a star of such size comes to its end. As we journey deeper into the life and death of Stephenson 218, we will explore its incredible scale, its discovery, and the incredible processes that govern its existence. From the moment it was born to the imminent supernova that awaits it, Stephenson 218 serves as a reminder of the vast and awe-inspiring forces that shape our universe. It challenges our understanding of stellar evolution and pushes the limits of what we thought was possible, giving us a glimpse into the extreme limits of cosmic scale. The discovery. How we found the largest star. In the vastness of space, some stars go unnoticed for centuries, their immense power and size hidden behind the thick curtains of cosmic dust and interstellar gas. Such was the case for Stephenson 218, the largest known star in the universe. For years, it sat in relative obscurity, yet its enormous presence obscured by the very material that forms stars and planets, the dust that clouds our view of the cosmos. But thanks to breakthroughs in technology and advances in infrared astronomy, this cosmic giant was eventually revealed to human eyes. In 2012, astronomers discovered something extraordinary. A star of unimaginable size, lying hidden within the Scutum constellation, deep in the heart of our Milky Way galaxy. The discovery was nothing short of a revelation. It was like finding a giant hiding behind a veil, its true size and power only visible through the sharpest of lenses. Until then, no one had ever fully grasped the true scale of the star we now call Stephenson 218. At the time of its discovery, astronomers had been searching the heavens for years, cataloging stars, measuring their light, and analyzing their distances. But even with all this data, many stars, especially the largest ones, had remained hidden. The reason? Interstellar dust. Much like a thick fog, cosmic dust clouds obscure our view of distant stars, making it almost impossible to see what lies behind. The dust grains scatter visible light, blocking the view of stars in much the same way that fog prevents us from seeing objects from a distance on Earth. This problem had long hindered astronomers' efforts to fully observe the most distant and massive stars in our galaxy. However, infrared astronomy changed everything. Unlike visible light, infrared light can pass through cosmic dust much more easily. It's like having the ability to peer through a fog using a special kind of light that scatters less, revealing objects that would otherwise remain invisible. And this breakthrough allowed astronomers to begin uncovering the secrets hidden within the dense clouds of gas and dust scattered throughout the Milky Way. The Gaia Space Observatory, launched by the European Space Agency in 2013, was a crucial tool in this discovery. The observatory's goal was simple yet ambitious: to create the most detailed three-dimensional map of our galaxy ever made. By measuring the positions, distances, and motions of over 1 billion stars, Gaia provided data that helped to pinpoint objects that were previously hidden from view. Among the stars it mapped was Stephenson 218, which had been lurking in the obscured Stephenson 2-star cluster, located some 20,000 light-years away from Earth. Before the advent of advanced infrared telescopes, most of our knowledge about distant stars was limited to the information we could gather from visible light. This gave us a basic understanding, but it was far from complete. The infrared spectrum opened up a new frontier of discovery, allowing astronomers to see through the dust and uncover the size, temperature, and composition of stars that had remained hidden for centuries. Using infrared data, astronomers were able to penetrate the veil of dust surrounding Stephenson 218 and measure its brightness and size, revealing a star so large that it immediately became the talk of the astronomical world. But how did scientists know they were looking at something truly extraordinary? How did they calculate that this was the largest star ever discovered? And the answer lies in the combination of cutting-edge infrared technology and a deep understanding of stellar physics, using a technique called parallax, which measures the apparent shift in a star's position as Earth orbits the Sun. Astronomers were able to calculate the distance to Stephenson 218 with remarkable precision. by measuring how much the star's position seemed to shift against the background of more distant stars, they were able to determine that it was indeed located around 20,000 light-years away, deep within the heart of the Milky Way. Once the distance was known, scientists used a method called angular diameter measurement to estimate the star's size. To understand this, imagine you are trying to measure a distant object, like a coin, across the world. Using advanced instruments, astronomers are able to measure how large a star appears from Earth, even though they can't directly measure its physical size due to the vast distance. The angular size tells them how big the star looks from our point of view. By combining this data with the distance calculation, scientists can then deduce the actual physical size of the star. At first, the results were difficult to believe. Stephenson 218 wasn't just large, it was enormous. The measurements confirmed that it had a radius roughly 2,150 times that of our Sun, making it one of the most massive stars ever observed. To put this into perspective, imagine the Sun as a basketball. If that basketball represented our Sun, Stephenson 218 would be the size of a sphere, more than 1,700 feet in diameter, taller than the Empire State Building. Its sheer volume is so vast that it could contain nearly 10 billion suns within its outer layers. To fully appreciate this discovery, you need to consider the scale of our solar system. If Stephenson 218 were placed at the center of the solar system, it would extend far beyond the orbit of Saturn, engulfing Mercury, Venus, Earth, Mars, Jupiter, and Saturn in its vast red-hot atmosphere. It would even dwarf our Sun, which is already a massive object by our standards. The discovery of a star of this size challenged everything we thought we knew about the limits of stellar growth. However, while the size of Stephenson 218 was shocking, it wasn't just its sheer magnitude that made this discovery so significant. The star's location in the Stephenson 2 cluster provided crucial insights into the life cycles of massive stars. This cluster, located within the Scutum constellation, is home to at least 26 other red supergiants, each one nearing the end of its life cycle. The presence of so many massive stars in such a small region of space raised important questions about how such stars are born, how they evolve, and how they eventually die. It also gave scientists the opportunity to study these stars in detail, comparing their size, temperature, and other characteristics to better understand the broader processes at play in stellar evolution. The discovery of Stephenson 218 wasn't just a victory for infrared technology. It also marked a turning point in our understanding of stellar evolution. Until this point, we had assumed that stars of such massive size were rare and perhaps even impossible. The size of Stephenson 218 seemed to push the boundaries of what we thought was possible for a star. Yet, here it was, a red supergiant that defied all expectations. But how did it get this big? Why does Stephenson 218 continue to grow, consuming vast amounts of energy and fuel? To answer these questions, scientists had to examine the star's internal structure and the forces that drive its expansion. The answer lies in the intense pressure and heat at the core of the star, combined with the fusion of increasingly heavy elements. In the case of red supergiants, this fusion process causes the star to burn through its fuel much more quickly than smaller stars. The result is a star that expands outward at an exponential rate, consuming vast amounts of fuel while burning through heavier and heavier elements until it reaches its final stage. Even more fascinating, the discovery of Stephenson 218 revealed that the star was not just larger than anything we had ever seen. It was also unlike any other star in the way it interacted with its environment. Unlike smaller stars, which remain relatively stable throughout their lifetimes, red supergiants like Stephenson 218 pulsate, expanding and contracting as they burn through their fuel. This pulsating behavior is a key feature of red supergiants and helps explain why Stephenson 218 continues to grow to such immense proportions. However, the discovery of this colossal star raised new questions about the very nature of star formation and evolution. Could there be other stars like Stephenson 218 that remain hidden in the farthest reaches of space, waiting to be uncovered by new technology? And if so, how many of them are out there? So for now, Stephenson 218 holds the title of the largest known star in the universe. But its discovery opened the door to a whole new realm of possibilities. As we continue to explore the universe, it's clear that there is so much more to learn. The story of Stephenson 218 is far from over. In fact, it is only just beginning. As technology improves and our understanding of the cosmos deepens, we may one day find that there are even larger stars hidden in the darkness, waiting to be discovered. The universe is vast, and we've only just scratched the surface. A stellar giant. Understanding the size of Stephenson 218. Imagine, for a moment, standing on the surface of a star, a vast, burning sphere of gas, radiating light and energy into the universe. Now, consider this. The star you're standing on is Stephenson 218. A red supergiant so large that it challenges the very limits of our understanding of stellar physics. Its size isn't just large, it's truly mind-boggling. To comprehend the scale of Stephenson 218, we have to break down its immense size and put it into perspective using comparisons to stars we already know, like our own sun. The first thing to understand is that Stephenson 218 is not a typical star. While most stars, including our sun, are considered average in size, Stephenson 218 belongs to a different class entirely. The red supergiants. These stars are at the end of their evolutionary cycle, burning through their fuel at an accelerated rate and expanding outward into enormous sizes as they near their death. It is in these final stages that stars like Stephenson 218 grow to unfathomable proportions. The Stephenson 218 is so large that if it were placed at the center of our solar system, it would completely engulf the orbit of Mars, Jupiter, and even Saturn. Its outer surface would stretch far beyond Saturn's orbit, swallowing all of the planets between it and the Sun. To help visualize this, consider the following. If our Sun were the size of a basketball, Stephenson 218 would be the size of a sphere more than 1,700 feet in diameter, roughly the height of the Empire State Building. In fact, it's so massive that we could fit nearly 10 billion suns inside it, making it not just the largest known star, but one of the most astonishing objects in the universe. The size of Stephenson 218 is estimated to be about 2,150 times the radius of our Sun. To put this into further perspective, the radius of the Sun is about 696,340 kilometers, 432,685 miles. Multiply that by 2,150, and we get a star with a radius of 1.4 million kilometers, 870,000 miles. A truly staggering number. To imagine this in physical terms, if you placed Stephenson 218 at the center of the solar system, its outer surface would extend past the orbit of Saturn, completely obliterating all the planets up to and including Saturn. Now, let's turn to the volume of Stephenson 218, which is even more incredible. Its volume is nearly 10 billion times that of the Sun, making it an unimaginable mass of gas and energy. If you were to attempt to fit the Sun into the space occupied by Stephenson 218, it would be like trying to fit a grain of sand into a beach. This massive star has so much volume that it could easily contain millions of Earths inside it without even coming close to filling up its vast interior. It's important to note that despite this overwhelming size, Stephenson 218 isn't dense. In fact, the density of red supergiants is incredibly low. The star's outer layers are so diffuse and stretched out that they are almost insubstantial compared to smaller stars like the Sun. In fact, the outer atmosphere of Stephenson 218 is far less dense than the Earth's atmosphere. This low density is due to the fact that red supergiants like Stephenson 218 have expanded so much that their material has spread thinly across an enormous area, even though their total mass is enormous. So why does a star like Stephenson 218 grow so large? It's all about how these stars consume and burn their fuel. When a star like Stephenson 218 runs out of hydrogen to burn in its core, it begins to burn heavier elements like helium, carbon, and oxygen. As these processes take place, the star's core contracts, causing the outer layers to expand and cool. This is when stars like Stephenson 218 start to take on their signature red color. The expansion process continues until the star grows into a red supergiant, with outer layers that are vastly spread out and highly unstable. But while its outer layers are cool compared to the Sun, its core is a much hotter place. Stephenson 218's core temperature reaches several million degrees Celsius, which allows the star to continue fusing heavier elements and producing the energy that keeps the star from collapsing under its own gravity. This intense fusion process generates massive amounts of energy. But it's this very process that eventually leads to the star's demise. Stephenson 218 is burning through its fuel at such an accelerated rate that it won't be able to sustain itself for long. In astronomical terms, it's living a short and violent life, and it's only a matter of time before it collapses into a supernova. But before we get to the spectacular end of this star, it's important to understand the impact of its size on its life cycle. Stars like Stephenson 218 burn through their fuel much faster than smaller stars. For example, while our Sun has been burning for about 4.6 billion years and will continue for another 5 billion years, a star like Stephenson 218 will only live for about 10 million years, a mere flash in the cosmic timeline. This rapid aging process is what makes these stars so extraordinary, and it's why they reach such enormous sizes in the final stages of their lives. In addition to their size, red supergiants like Stephenson 218 also exhibit fascinating pulsation behavior. As the star burns through its fuel and undergoes various stages of fusion, it begins to expand and contract over time. This pulsation is a characteristic feature of red supergiants. It happens as the outer layers of the star respond to changes in temperature and pressure, causing the star to expand outward and then contract back inward. These pulsations contribute to the instability of the star, making it even more prone to eventual collapse. Despite its massive size, Stephenson 218's outer layers are incredibly unstable. This instability is not unique to Stephenson 218. All red supergiants exhibit this behavior, as their massive size and energy production result in constant fluctuations in their internal pressure. These fluctuations cause the star to experience dramatic changes in size, with its outer layers expanding and contracting over periods of years or even decades. However, this pulsation behavior is just one piece of the puzzle. The final stages of a red supergiant's life, like Stephenson 218, involve the gradual depletion of its fuel supply. As the star burns through heavier and heavier elements, it moves closer to the point where it can no longer sustain the fusion process. Eventually, the core will collapse under its own weight, and the star will explode in a supernova. This explosion will release an unimaginable amount of energy, and the shock wave will spread through space, scattering elements like iron, carbon, and oxygen across the galaxy. These elements will eventually form new stars, planets, and, potentially, the building blocks of life. The immense size of Stephenson 218 is also significant for another reason. It helps us understand the role of massive stars in the universe. Stars like Stephenson 218 are responsible for producing the heavy elements that make up the planets and the very building blocks of life itself. Without these giant stars, we wouldn't have the carbon, oxygen, and iron that are essential to life on Earth. This cosmic cycle of birth, life, death, and rebirth is a fundamental process that drives the evolution of galaxies, solar systems, and ultimately, life itself. The size of Stephenson 218 also provides insight into the way stars influence their surroundings. The immense gravity of a star this large has a profound impact on the formation of nearby stars and planets. As Stephenson 218 burns through its fuel, it creates powerful winds that blow material into space, enriching the interstellar medium with heavier elements. These elements then form new stars and planets, creating a cycle of stellar birth and death that shapes the very fabric of the universe. As we continue to explore the vastness of the cosmos, Stephenson 218 serves as a reminder of the incredible scale of the universe. It is a testament to the immense power and energy of red supergiants, stars that live fast, burn bright, and die in spectacular fashion. But while its size is remarkable, the true beauty of this discovery lies in what it tells us about the universe's most fundamental processes: the birth of stars, the fusion of elements, and the ongoing evolution of galaxies and life itself. How we measure stellar sizes, the science behind the numbers. Understanding the size of a star like Stephenson 218 is no simple task. In fact, measuring a star's size, especially one as large and distant as Stephenson 218, is one of the most complex challenges in modern astronomy. To the untrained eye, stars might all seem like distant points of light in the night sky. However, astronomers know that these points of light can represent enormous spheres of burning gas, each with its own unique size, temperature, and life cycle. For some stars, like Stephenson 218, determining their exact size requires a combination of intricate measurements, advanced technology, and years of research. The key to measuring a star's size lies in understanding its distance from Earth and its angular diameter. The distance to a star is one of the most crucial pieces of information needed to determine its true size. If you think about it, measuring the size of a star is a bit like trying to estimate the size of a distant object on Earth, say, a mountain or a building. If you know how far away it is and how large it appears in the sky, you can calculate its actual size. The closer the object is, the easier it is to see its true size. The farther away it is, the more difficult it becomes to measure, as it appears smaller and smaller. Astronomers rely on several methods to calculate the distance to stars, and one of the most important is parallax. Parallax involves measuring the apparent shift in a star's position as Earth orbits around the Sun. Just as a nearby object appears to move against the background when you shift your perspective, stars closer to us appear to shift position relative to the more distant stars when viewed from opposite sides of Earth's orbit. By measuring this shift, astronomers can determine the distance to the star with remarkable accuracy. This technique is particularly useful for stars that are within a few thousand light-years from Earth, and it was an essential tool in determining the distance to Stephenson 218. However, Stephenson 218 is located approximately 20,000 light-years away, which is far beyond the range of traditional parallax measurements. To measure a star at this distance Astronomers must rely on indirect methods and models that use both parallax and data from infrared observatories. This is where technologies like the Gaia Space Observatory and Spitzer Space Telescope come into play. Infrared telescopes are able to detect light that is invisible to the human eye. Unlike visible light, which is blocked by cosmic dust, infrared radiation can pass through these obstacles. This is particularly important when studying stars like Stephenson 218, which are located behind thick clouds of interstellar gas and dust. Using infrared technology, astronomers can look past the clouds and measure the star's brightness and size. The Spitzer Space Telescope was crucial in this respect, allowing astronomers to see through the dust and obtain accurate measurements of the star's brightness and size. Once the distance is known, the next challenge is determining the angular diameter of the star. The angular diameter refers to the apparent size of the star as seen from Earth. For a star like the Sun, measuring its angular diameter is relatively simple because it's close enough for us to see its size clearly. But for a distant star like Stephenson 218, this measurement requires sophisticated tools. One of the most advanced tools used in measuring a star's angular diameter is interferometry. Interferometry works by combining the light from multiple telescopes to create a much larger, more powerful virtual telescope. The technique relies on the fact that light from a star behaves like waves. By measuring the interference patterns produced when the light from two or more telescopes is combined, astronomers can calculate the star's angular diameter with a high degree of precision. This method is one of the most accurate ways to measure the size of distant stars, and played a key role in determining the dimensions of Stephenson 218. However, even with these advanced techniques, measuring a star of Stephenson 218's size comes with its own set of challenges. The star's immense distance and the complexity of its outer layers make it difficult to pinpoint its exact size. Because Stephenson 218 is a red supergiant, its outer layers are diffuse and tenuous, making them harder to measure compared to more compact stars. The vastness of its outer layers means that its boundaries are not as clearly defined as those of smaller stars. Instead of having a sharp boundary, red supergiants like Stephenson 218 have outer layers that gradually fade into space, which makes determining where the star ends and space begins a tricky task. Despite these challenges, astronomers have been able to estimate Stephenson 218's size with remarkable accuracy. Through a combination of infrared data, angular measurements, and advanced modeling techniques, scientists have determined that Stephenson 218 has a radius about 2,150 times the radius of our Sun. This makes it one of the largest stars ever discovered. To put this into perspective, if the Sun were placed in the center of our solar system, it would stretch just past the orbit of Mercury, with the entire inner solar system contained within its outer layers. In contrast, Stephenson 218 would stretch far beyond the orbit of Saturn, engulfing all of the planets within its massive atmosphere. This measurement is not just a number. It has profound implications for our understanding of stellar evolution and the life cycle of massive stars. The size of Stephenson 218 indicates that it is in the final stages of its life, slowly burning through its fuel at an accelerated rate. The more massive a star is, the faster it burns its fuel, and the faster it dies. Stephenson 218 is an example of a star living a fast, intense life, burning through its fuel at a rate that smaller stars like our Sun will never approach. But the implications of this discovery extend beyond Stephenson 218 itself. The techniques used to measure this star are crucial for understanding other massive stars in the universe, many of which are still hidden behind cosmic dust. By developing more advanced methods for measuring distant stars, astronomers will be able to study a whole new class of objects, red supergiants, hypergiants, and other massive stars that were previously beyond our reach. These stars play a central role in the evolution of galaxies, the formation of new stars, and the creation of the heavy elements that make up planets and, ultimately, life. The measurements of Stephenson 218 also challenge our assumptions about the limits of stellar size. For years, astronomers believed that there was a natural upper limit to how big a star could grow. Stephenson 218 pushes this boundary further than we ever imagined, forcing scientists to rethink the models of stellar formation and evolution. As we study this enormous star and others like it, we may eventually uncover new principles of stellar physics that can help us understand the very nature of the universe itself. As we look to the future, the quest to measure and understand stars like Stephenson 218 will continue. New technologies, including more powerful infrared telescopes and space-based observatories, will allow us to uncover more hidden giants in the universe and refine our measurements even further. We may one day find stars that are even larger than Stephenson 218, hidden in the farthest reaches of space, waiting to be discovered. In the coming years, the continued study of these cosmic giants will deepen our understanding of the universe's most fundamental processes. The discovery of Stephenson 218 has opened a new chapter in our study of the cosmos, a one that challenges everything we thought we knew about the stars. The journey of discovery, though remarkable so far, has only just begun. The nature of red supergiants. Why Stephenson 218 is so large. To understand why Stephenson 218 is so massive, we need to step back in time and look at the life cycle of stars, particularly the life cycle of red supergiants like Stephenson 218. These stars follow a very different evolutionary path than smaller stars like our Sun. While the Sun will spend billions of years in a stable phase, burning hydrogen into helium in its core, a star like Stephenson 218 burns through its fuel at an astonishing rate, which leads to its rapid growth and eventual transformation into a supergiant. At the core of every star is a process of nuclear fusion, where hydrogen atoms are fused together to form helium and releasing enormous amounts of energy in the process. This energy counteracts the force of gravity, preventing the star from collapsing inward. For smaller stars, this balance lasts for billions of years. The Sun, for instance, is expected to remain stable for another 5 billion years before it enters the next phase of its life cycle. However, for massive stars like Stephenson 218, this process unfolds much more quickly. The reason massive stars like Stephenson 218 live such short, intense lives is due to their rate of fuel consumption. The larger the star, the faster it burns through its hydrogen. Stars with masses greater than 8 times that of the Sun, like Stephenson 218, burn through their fuel at a rate that is hundreds of times faster than the Sun. This rapid consumption of hydrogen leads to an early, dramatic expansion in the star's size as the outer layers begin to cool and expand while the core contracts under gravity. As Stephenson 218 runs out of hydrogen to burn in its core, it begins to fuse heavier elements. First, it begins to burn helium, then carbon, oxygen, and eventually heavier elements. This process releases even more energy, but the energy produced is not enough to maintain the balance between the force of gravity and the outward push of radiation. This imbalance causes the star to expand rapidly, leading to the red supergiant phase, where the star grows to incredible sizes. Stephenson 218's transformation into a red supergiant is a direct result of this runaway fusion process. In the red supergiant phase, the star's core continues to contract and heat up, while the outer layers cool and expand. The star's outer atmosphere becomes so diffuse and extended that its density decreases dramatically. The massive expansion of the outer layers is a critical characteristic of red supergiants. These stars are incredibly large, but their outer layers are very low in density, which is why they can grow so vast without collapsing under their own gravity. But the size of a red supergiant like Stephenson 218 isn't just about the amount of fuel it consumes. It's also about the physics of stellar pressure and energy transport. In stars like Stephenson 218, the core continues to burn heavier elements, and this causes a tremendous buildup of energy within the core. As the core contracts under gravity, it creates an intense pressure that forces the outer layers to expand. The outer envelope of the star, which is made up of cooler, less dense material, gets stretched farther and farther from the core, contributing to the star's incredible size. This process continues until the star reaches a point where its outer layers are so diffuse that the star's overall density becomes a fraction of that of smaller stars. At this stage in its evolution, Stephenson 218 is a classic red supergiant, a massive, cool, and unstable star that is nearing the end of its life. It is a star that has exhausted its primary fuel source, hydrogen, and is now living on its secondary fuels, burning through helium, carbon, and oxygen. As this process continues, Stephenson 218's size will continue to increase, but it will not expand forever. The star is gradually running out of fuel, and when it finally reaches the point where it can no longer sustain fusion, it will face a catastrophic collapse that will lead to its final stage, a supernova explosion. The formation of red supergiants like Stephenson 218 is part of a larger cycle in stellar evolution. Stars like Stephenson 218 are born from massive clouds of gas and dust. Over millions of years, gravity causes the material in these clouds to collapse inward, forming a new star. This star begins its life as a massive blue giant, burning hydrogen in its core and radiating immense amounts of energy. Over time, as the star runs out of hydrogen and begins to burn heavier elements, it moves through various phases, from blue giant to red supergiant. Finally, when it reaches the red supergiant phase, it has burned through almost all of its fuel and is in the final stages of its existence. At this point, the star's core becomes unstable, and the star will ultimately explode in a supernova. The life cycle of red supergiants like Stephenson 218 has profound implications for the universe as a whole. These stars are not just large, they are also incredibly important for the formation of the elements that make up the universe around us. When Stephenson 218 eventually explodes as a supernova, it will scatter heavy elements like iron, carbon, and oxygen throughout the interstellar medium. These elements will eventually become part of new stars, planets, and even life itself. In this sense, the death of stars like Stephenson 218 is what fuels the ongoing cycle of star formation and the creation of planets and life in the universe. As massive stars evolve into red supergiants, their size and mass become significant factors in how they influence their surroundings. The gravitational influence of a red supergiant like Stephenson 218 is immense, and it can affect the formation of nearby stars and planetary systems. As it burns through its fuel, the star sheds material into space through stellar winds, powerful streams of charged particles that flow out from the star's outer layers. These stellar winds carry away much of the star's mass and energy, enriching the interstellar medium with heavy elements. These elements will eventually become part of new generations of stars, continuing the cycle of cosmic evolution. Stephenson 218, like other red supergiants, has reached the final stages of its life, where it will soon begin to collapse in on itself. This collapse will eventually lead to the formation of a supernova. But the processes leading to this collapse are what makes Stephenson 218 so fascinating. The immense size of the star and the speed at which it burns through its fuel have led to the rapid evolution of this stellar giant. As it moves toward its final stages, Stephenson 218 becomes a remarkable example of the forces that govern the birth, life, and death of stars. For astronomers, understanding the life cycle of stars like Stephenson 218 is crucial for understanding the larger processes of star formation and the creation of heavy elements in the universe. By studying massive stars in their final stages, scientists gain insight into the mechanics of stellar death and the formation of new stars. They also learn more about the processes that have shaped the universe as we know it. The formation of galaxies, solar systems, and even life itself. The discovery of Stephenson 218 and other red supergiants has opened a new chapter in our understanding of stellar evolution. These massive stars were at the edge of what we thought was possible, and their size, energy, and explosive death provide critical clues about the nature of the universe. As we study these giants, we continue to uncover the fundamental processes that govern the birth and death of stars, and ultimately, the creation of the elements that make up everything around us. The pulsing heart. Why red supergiants like Stephenson 218 expand and contract? As we continue to explore the vastness of Stephenson 218, it becomes evident that its size and instability are not the only factors that make it so extraordinary. This stellar giant is also an example of a much more complex behavior exhibited by red supergiants. Pulsation. Unlike many other stars, which maintain a relatively stable size and luminosity, red supergiants like Stephenson 218 exhibit a cyclical pattern of expansion and contraction, with their outer layers swelling outward before collapsing back inward in a rhythmic dance that continues throughout their lives. This pulsating behavior is not random. Rather, it is driven by the complex interplay of forces within the star's interior. It's important to note that pulsation in stars like Stephenson 218 is a direct result of the processes that occur deep inside the star, in its core, and the delicate balance of energy production and gravitational forces that governs the star's evolution. At the heart of this pulsating cycle is the energy production taking place in the core of Stephenson 218. As this star burns through its fuel, first hydrogen, then helium, and ultimately heavier elements like carbon and oxygen, the fusion reactions generate immense amounts of energy. This energy pushes outward, counteracting the force of gravity and maintaining the star's shape. However, as the fusion process slows down and the star begins to burn heavier elements, the core becomes increasingly unstable. As the core contracts under the force of gravity, the outer layers of the star are pushed outward, causing the star to expand. When the outer layers are pushed outwards, the temperature of the star's surface drops, and it becomes cooler, turning the star red. This expansion, however, is not permanent. The energy production inside the core is constantly fluctuating, and as it decreases, the outward pressure weakens, causing the star to collapse inward once again. This results in a contraction of the outer layers, which causes the surface temperature to increase and the star to appear brighter, pushing the cycle back toward expansion. This process of expansion and contraction is not immediate. It happens slowly, over the course of years or even decades. The pulsations of Stephenson 218 are not like the regular heartbeat of a human heart. Rather, they are slow and uneven cycles that last for many years, with periods of expansion and contraction interspersed with periods of relative stability. This behavior is not unique to Stephenson 218, but is characteristic of most red supergiants. These stars, in their final stages, are constantly fluctuating in size and energy output, never settling into the quiet stability of younger stars like the Sun. But what drives this pulsation cycle? The answer lies in the way energy is transported through the star's layers. In stars like Stephenson 218, energy produced by nuclear fusion in the core has to travel outward to the star's surface. The outer layers of a red supergiant are so large and diffuse that they cannot efficiently transport energy through radiation alone, as smaller stars can. Instead, the energy is transported by a combination of radiation and convection. Convection occurs when hot gas from the core rises toward the surface, while cooler gas from the surface sinks back down toward the core. This process helps to transfer energy outward, but it also contributes to the star's pulsations. As energy builds up in the core, it causes the outer layers to expand. When the convection process slows down, the outer layers contract. When this cyclical process causes the star to oscillate in size, expanding and contracting over time. The pulsation of a star like Stephenson 218 is also influenced by the star's luminosity and temperature. As the outer layers expand, the star becomes cooler and dimmer, while contraction causes the temperature and luminosity to rise. These fluctuations in brightness and temperature are one of the reasons why red supergiants like Stephenson 218 appear so different from stars like the Sun. While the Sun's luminosity remains relatively constant over long periods of time, the brightness of red supergiants can change significantly as they undergo these pulsations. This pulsating behavior plays a crucial role in the star's evolution and its eventual fate. As Stephenson 218 continues to pulsate, it loses material through a process known as stellar wind. This is a continuous outflow of gas and particles from the star's outer layers, driven by the intense radiation pressure produced by the star's fusion reactions. The pulsations of the star contribute to the strength of the stellar wind, which gradually strips away the outer layers of the star, further diminishing its mass over time. While this pulsating behavior is fascinating, it also makes the star inherently unstable. The constant expansion and contraction of the outer layers puts a great deal of strain on the star's structure, and eventually, this instability will lead to the star's dramatic collapse. As the pulsation cycles continue, the star becomes increasingly unstable, and its outer layers become more diffuse. The outer layers of Stephenson 218 will eventually be expelled into space, carrying with them the heavy elements that the star has created during its lifetime. As Stephenson 218 continues to pulsate, it is also shedding material into the interstellar medium, enriching the gas and dust that will eventually form new stars, planets, and perhaps even life. The process of pulsation and material loss plays a vital role in the cosmic recycling process, ensuring that the elements formed inside stars like Stephenson 218 are distributed throughout the galaxy and used to create future generations of stars and planetary systems. Despite its immense size and power, Stephenson 218 is living on borrowed time. The pulsating behavior, along with the massive loss of material through stellar winds, means that the star's mass is slowly decreasing, and its fuel is running out at an accelerated rate. In just a few million years, Stephenson 218 will exhaust its nuclear fuel and enter its final, explosive stage, the supernova. When this happens, it will release an unimaginable amount of energy, outshining an entire galaxy for a brief moment in time. But before that explosive end, Stephenson 218 will continue to expand and contract, its outer layers pushing outward in a cyclical rhythm that is both beautiful and chaotic. These pulsations are a reminder of the immense power and instability that govern the lives of the universe's most massive stars. In the case of Stephenson 218, these pulsations are part of its slow, inevitable journey toward its death. A death that will leave behind a spectacular supernova and forever change the cosmic landscape. The final stages of a red supergiant. The death of Stephenson 218. All stars, no matter how massive or bright, have a finite lifespan. Just like human beings, they are born, live, and eventually die. For a star like Stephenson 218, however, the death will be far more dramatic and violent than any human could imagine. The end of such a massive star is inevitable, while smaller stars like our Sun will have a gradual demise, swelling into red giants before shedding their outer layers and becoming white dwarfs. A star like Stephenson 218 will undergo a much more violent end. It will explode in a supernova, releasing a tremendous amount of energy that will outshine an entire galaxy for a brief period of time. But before Stephenson 218 reaches this violent conclusion, it must first complete the process of burning through its available fuel. A star's journey toward death is largely defined by the fuel it uses. Like a car that consumes gas, stars rely on the fusion of elements at their cores to produce the energy that powers them. For most of a star's life, it burns hydrogen into helium through nuclear fusion. In a star like the Sun, this process will last for billions of years. However, for massive stars like Stephenson 218, the fusion process is much faster. These stars burn through their fuel at an accelerated rate, meaning they live much shorter but more intense lives. Their massive size and immense internal pressure drive the rapid consumption of hydrogen and the subsequent burning of heavier elements. Once a red supergiant like Stephenson 218 exhausts its hydrogen supply, it turns to the fusion of heavier elements. The core contracts, causing the outer layers to expand. As Stephenson 218 continues to burn helium, carbon, and oxygen, it becomes increasingly unstable. The core of the star becomes hotter and denser as it attempts to sustain the fusion process. This eventually leads to the formation of an iron core. When a star like Stephenson 218 creates an iron core, it marks the beginning of the end. Iron, unlike lighter elements like hydrogen or helium, cannot undergo fusion to release energy. As a result, the core can no longer generate enough outward pressure to counterbalance the force of gravity. This is the critical point where a massive star's evolution takes a dramatic turn. The core of the star becomes so dense that it collapses under its own weight, triggering a catastrophic chain of events. As the core collapses, the outer layers of the star are violently expelled into space. The collapse of the core is incredibly rapid, happening in a matter of seconds, and the resulting shockwave propels the outer layers outward at an extraordinary velocity. The explosion that follows is what we call a supernova. A supernova is the most powerful explosion in the universe. It occurs when the core of a massive star collapses, causing an immense release of energy. This explosion can release as much energy in a single second as the star has emitted over its entire lifetime. The shockwave from the explosion is so intense that it can briefly outshine an entire galaxy, making it visible from great distances. In fact, when a star like Stephenson 218 explodes, its brightness can increase by a factor of billions, allowing astronomers to see the explosion from billions of light years away. The supernova is not only an incredible display of energy, but also an important process in the creation of heavy elements. During the supernova explosion, elements like iron, gold, and uranium are formed in the extreme conditions of the blast. As Stephenson 218 reaches the final stages of its life, its core begins to contract and become incredibly dense, and the outer layers are expelled at incredible speeds. The collapse of the core is so intense that the pressure and temperature in the core reach levels that are far beyond anything that could occur in a less massive star. This triggers a supernova explosion, which releases a burst of radiation and a shock wave of energy that destroys the star. The star's outer layers are ejected into space, while the remaining core may collapse into a black hole or a neutron star, depending on the mass of the original star. The supernova explosion marks the final death throes of Stephenson 218. During this cataclysmic event, the star's energy will be released in a spectacular burst of light and radiation. A light that could briefly outshine an entire galaxy. For a short time, this dying star will be one of the brightest objects in the universe, visible from billions of light years away. The sheer power of this explosion is almost beyond comprehension, releasing as much energy as the star has produced over its entire lifetime in a fraction of a second. This burst of energy will travel across the galaxy, dissipating into space, while the shock wave of the explosion will continue to push the outer layers of the star outward. As the outer layers of the star are ejected into space, the material that once formed Stephenson 218 is scattered across the interstellar medium. This material is rich in the elements that the star formed during its lifetime, and it will be incorporated into the formation of new stars, planets, and eventually, life. In this way, the death of a star like Stephenson 218 contributes to the ongoing cycle of stellar birth and death that drives the evolution of galaxies, solar systems, and life itself. The very atoms in our bodies may have been forged in stars like Stephenson 218 billions of years ago. The death of this giant star is not an end, but rather a beginning, a new chapter in the story of the universe. The aftermath of a supernova can vary depending on the mass of the star. For stars like Stephenson 218, which are massive enough to undergo the core collapse necessary for a supernova, the remnant left behind is often either a neutron star or a black hole. A neutron star is an incredibly dense object, so compact that a teaspoon of its material would weigh as much as a mountain. This dense core is the collapsed remnant of the star's core, left behind after the outer layers were ejected. In the case of Stephenson 218, if the core is massive enough, it could collapse into a black hole, a region of space where gravity is so intense that nothing, not even light, can escape its pull. Whether the remnant becomes a neutron star or a black hole, the supernova explosion of Stephenson 218 will leave behind an object that is incredibly dense and powerful. These remnants are often surrounded by nebulae, clouds of gas and dust left behind by the explosion. These nebulae contain the heavy elements that the star produced during its life, and they serve as the building blocks for future generations of stars and planets. In this way, the death of Stephenson 218 will ensure that the elements necessary for life and the formation of new stars will continue to be distributed throughout the universe. The supernova explosion of Stephenson 218 is a monumental event in the life of our galaxy. It will change the surrounding region of space, sending shock waves through the interstellar medium and triggering the formation of new stars. This process of stellar death and rebirth is part of the cosmic cycle that governs the evolution of the universe. The materials scattered by the explosion will eventually become part of new stars, planets, and galaxies, continuing the cycle of cosmic creation. The legacy of Stephenson 218 will live on, not just in the remnants left behind, but in the stars and planets that will form from the materials it has released. For now, Stephenson 218 continues its slow and inevitable march toward its final fate. Each pulsation, each expansion and contraction of its outer layers brings it closer to the point of no return. Eventually, its core will reach the point where it can no longer sustain the fusion process, and the star will collapse in on itself, triggering the supernova that will mark the end of this giant's life. But even in its death, Stephenson 218 will play an important role in shaping the future of the universe, providing the raw materials for the stars and planets that will follow. The death of this massive star will be a cosmic event that will resonate throughout space, a reminder of the incredible power and beauty of the universe's most massive objects. The aftermath. What happens after the supernova? The death of a star like Stephenson 218 is one of the most spectacular events in the universe. When it explodes as a supernova, the energy released will briefly outshine an entire galaxy. For a short time, Stephenson 218's final burst of light will dominate the skies, becoming one of the brightest objects visible in its corner of the Milky Way. But once the explosion subsides, the remnants of the star will begin to cool, and the dust and debris will spread across the cosmos. The question then becomes, what happens to the star's material after the supernova? What will become of Stephenson 218's legacy? The answer lies in a process known as cosmic recycling, where the death of a star gives birth to new material that will eventually form new stars, planets, and even life. But when a star like Stephenson 218 dies, it doesn't just vanish. It leaves behind a rich legacy of elements that have been created during its lifetime and in the explosion that marks its death. These elements, such as iron, carbon, oxygen, and nitrogen, are the building blocks for everything in the universe. Without supernovae, like the one Stephenson 218 will undergo, the elements that make up planets and life would never exist. In this way, every supernova contributes to the ongoing creation of the universe. When the core of Stephenson 218 collapses into a supernova, the intense pressure and heat will forge new elements. Heavier elements like iron and gold are produced in the fiery crucible of the supernova explosion, creating the very building blocks for future generations of stars and planets. These elements are crucial not just for the formation of new stars, but also for the formation of solid bodies like planets, moons, and asteroids. In a sense, the death of a star like Stephenson 218 is a gift to the universe, providing the raw materials that will eventually give rise to new solar systems and, possibly, new forms of life. The explosion of a star like Stephenson 218 will scatter these elements into the interstellar medium, the vast, empty space between stars in the galaxy. This material will mix with the surrounding gas and dust, enriching the interstellar medium with heavier elements. Over time, this enriched material will form new molecular clouds, the birthplace of future stars. When these clouds of gas and dust collapse under their own gravity, they will form new stars, continuing the cycle of stellar birth and death that has been ongoing for billions of years. In this way, the explosion of Stephenson 218 will play a role in the next generation of stars and planetary systems. But the story doesn't end there. The material expelled during the supernova explosion will not only form new stars, it will also contribute to the formation of planets. As the gas and dust settle and cool, it will begin to condense into solid bodies. The heavier elements produced during the supernova, like iron and carbon, will form the cores of new planets, while lighter elements will form their atmospheres. This process is part of a continuous cycle in the universe, where the death of one generation of stars leads to the birth of the next. Without supernovae like that of Stephenson 218, planets as we know them would never form. When in addition to enriching the interstellar medium with the elements necessary for planet formation, the shock wave from the supernova will also trigger the formation of new stars. The explosion creates a sudden, intense release of energy that compresses the surrounding gas and dust, causing it to collapse and form new stars. This process, known as triggered star formation, is one of the ways in which the death of a massive star like Stephenson 218 can create new stellar nurseries. The shock wave from the supernova explosion will provide the necessary conditions for nearby clouds of gas and dust to collapse, giving rise to new stars, planets, and solar systems. The remnants of Stephenson 218, once its supernova has subsided, will be scattered throughout the galaxy. What remains of the star's core will either become a neutron star or collapse into a black hole. If the core's mass is between 1.4 and 3 times the mass of the Sun, it will form a neutron star, a dense, incredibly compact object that is composed almost entirely of neutrons. Neutron stars are fascinating objects, with magnetic fields that are trillions of times stronger than the Earth's, and they rotate at speeds close to the speed of light. These remnants of the star are incredibly dense. Just a teaspoon of neutron star material would weigh as much as a mountain. If Stephenson 218's core is massive enough, however, it will collapse into a black hole. A black hole is a region of space where gravity is so strong that not even light can escape its pull. The core of Stephenson 218 will collapse to an infinitesimal point, creating a singularity, an object of infinite density. Black holes are some of the most enigmatic objects in the universe, and their presence in the remnants of a star like Stephenson 218 would mark the end of this particular star's life, but not the end of its influence on the cosmos. Even in death, the remnants of Stephenson 218 will continue to influence the galaxy. The shock waves from the supernova will travel out into space, colliding with other clouds of gas and dust, potentially triggering new star formation. The elements produced by the supernova will mix with the surrounding material, creating new generations of stars, planets, and possibly life. In this way, the death of Stephenson 218 will be a catalyst for the continued evolution of the galaxy. This cosmic recycling process is one of the most important aspects of stellar death. Stars like Stephenson 218 don't just die and disappear. They leave behind a legacy of material that will be used to create new stars and planets. Without this cycle, the universe would lack the heavy elements that make up everything from the Earth to the life that inhabits it. The very elements in our bodies, carbon, nitrogen, oxygen, were likely formed in stars like Stephenson 218 and were spread throughout the universe when those stars died. In this sense, we are all made of stardust, the remains of stars that exploded billions of years ago. But what happens to the supernova remnant after the initial explosion? As the material from the explosion spreads out into space, it forms a supernova remnant, a vast cloud of gas and dust that is expanding outward. Over time, this remnant will cool and disperse, and the elements it contains will eventually become part of new molecular clouds. These clouds will continue the cycle of star formation, eventually giving rise to new stars, new planetary systems, and possibly even new forms of life. The death of Stephenson 218 will mark the end of one chapter in the universe's story, but it will also be the beginning of the next chapter. As the dust settles and the shock waves dissipate, the legacy of Stephenson 218 will live on in the stars and planets that it helped to create. Its death will enrich the universe with the heavy elements necessary for life, and its explosive end will give rise to new generations of stars and galaxies. In a way, the universe is a giant recycling machine, constantly renewing itself and creating new stars and planets from the remnants of those that came before. The death of Stephenson 218 will be a part of this ongoing cycle, ensuring that the elements necessary for life continue to be spread throughout the cosmos, paving the way for the stars and planets of tomorrow. The cosmic legacy. How the death of Stephenson 218 will shape the universe. The death of a star like Stephenson 218 is far more than just an isolated event. It is a cosmic spectacle, a dramatic and cataclysmic conclusion to a star's life. But it is also part of a much larger process, one that continues to shape the universe in profound ways. The explosion of Stephenson 218 will be one of the most powerful events in the galaxy, releasing an immense amount of energy and scattering the star's elements across vast distances. But this explosion isn't just a violent end. It is also the beginning of something new. Yet when Stephenson 218 reaches the end of its life and explodes as a supernova, it will release a staggering amount of energy, far more than the star has emitted in its entire life. This release of energy will momentarily outshine an entire galaxy, sending shockwaves rippling through space. These shockwaves will travel across the cosmos, interacting with nearby clouds of gas and dust, and triggering the formation of new stars. The death of Stephenson 218 will be a key moment in the ongoing process of star formation in our galaxy, creating the conditions necessary for new stellar nurseries to form and giving rise to the next generation of stars. In the aftermath of the explosion, the elements that Stephenson 218 created during its life, heavy elements like carbon, oxygen, iron, and nitrogen, will be scattered across the interstellar medium. This material, which was forged in the heart of the star during its nuclear fusion process, will be the building blocks for future generations of stars and planets. The elements produced by Stephenson 218 will be incorporated into new molecular clouds, where they will contribute to the formation of new stars and planetary systems. This process of stellar death and rebirth is known as cosmic recycling. It is an ongoing cycle in the universe, where the death of one generation of stars leads to the birth of the next. The heavy elements that make up the planets we live on, and the elements in our bodies, were all created in stars like Stephenson 218 and scattered throughout the galaxy during supernovae. Without these explosions, the universe would lack the building blocks necessary for the formation of planets, moons, and even life itself. The creation of these heavy elements is a fundamental part of the life cycle of the universe. When a star like Stephenson 218 explodes, it produces elements that are heavier than iron, which are formed in the extreme conditions of a supernova explosion. These elements are ejected into space, enriching the surrounding gas and dust. Over time, this enriched material will become part of new stars, planets, and even new solar systems. This is the cosmic cycle of creation and destruction, where the death of one generation of stars ensures the creation of the next. The elements formed in stars like Stephenson 218 are essential for the formation of life, and they are passed on through the universe from one generation to the next. In this way, Stephenson 218's death will be a crucial moment in the evolution of the Milky Way galaxy. The shock waves from its supernova will provide the necessary energy to trigger the collapse of nearby gas and dust clouds, creating the conditions for new stars to form. These new stars, in turn, will create new planetary systems, some of which may even support life. In this sense, the death of Stephenson 218 will directly contribute to the future of our galaxy and the evolution of the universe. The energy and material released by the supernova will act as a catalyst for future star formation, ensuring that the cycle of creation and destruction continues. But it's not just the formation of stars that is influenced by the death of a giant like Stephenson 218. It's the creation of planets. When the supernova's shockwave sweeps through the surrounding gas and dust, it compresses the material, causing it to collapse inward and form new stars. As this gas and dust continues to condense, it eventually cools and begins to form solid bodies. The heavy elements created by Stephenson 218 will become part of these solid bodies, forming the cores of new planets and moons. The death of Stephenson 218 will help give birth to new worlds, some of which may one day host life. This process of star formation and planetary creation is part of the ongoing cosmic recycling process that has been occurring in the universe for billions of years. Stars like Stephenson 218 are not just massive objects that live fast and die young. They are essential to the formation of new stars and planets. They create the heavy elements that are needed to form planets, and their explosions provide the energy that triggers the formation of new stars. The universe is constantly renewing itself, with each generation of stars giving rise to the next. The death of Stephenson 218, like the death of any massive star, marks the end of its life. But it also marks the beginning of something new. The material expelled by the supernova will become part of new stars and planets, creating the conditions necessary for the formation of new solar systems. In a way, the death of Stephenson 218 will create the seeds for future generations of stars and planets. This process of cosmic recycling is essential to the evolution of galaxies and the universe as a whole. Even though Stephenson 218's death will be a violent and dramatic event, it is not the end of its legacy. The elements created by the star during its lifetime will continue to have a profound impact on the universe, ensuring that new stars and planets will be born from its remains. The death of Stephenson 218 will contribute to the ongoing process of star formation and planetary creation, ensuring that the universe continues to evolve and create new worlds. But the influence of Stephenson 218's death won't stop there. As the shock waves from the supernova travel through space, they will interact with other molecular clouds, triggering the formation of new stars and planetary systems. These shock waves will spread across the galaxy, seeding the interstellar medium with the elements necessary for the formation of new stars and planets. The universe will continue to evolve, with each supernova explosion adding to the pool of material available for new generations of stars and planets. Stephenson 218's death is a cosmic event, but it is also part of a much larger story, one that stretches across billions of years. But the elements formed in stars like Stephenson 218 have been scattered throughout the universe, and they will continue to shape the future of galaxies, solar systems, and even life itself. The process of star formation, death, and rebirth is ongoing, and each generation of stars adds to the richness and diversity of the universe. The death of Stephenson 218 will contribute to the next generation of stars, planets, and possibly even life. As we look to the future, the death of Stephenson 218 reminds us of the immense forces that shape the universe. Stars like Stephenson 218 are the engines of creation in the universe, forging the elements that make up everything around us. Their deaths are not the end, but the beginning of something new. A new generation of stars and planets, and perhaps new forms of life. This cosmic cycle of creation, a destruction, and rebirth will continue long after Stephenson 218's supernova fades into the darkness of space. The universe, in its endless expansion, will continue to evolve, driven by the forces that have governed it since the beginning of time. The role of massive stars in the universe. How stars like Stephenson 218 shape galaxies and life. In the grand scale of the cosmos, stars like Stephenson 218 are not just monumental objects. They are the architects of the universe. These massive stars play a crucial role in shaping galaxies, seeding the cosmos with the building blocks of new stars, planets, and even life itself. Their life cycle, from formation to death, is intricately linked to the evolution of galaxies, solar systems, and the very fabric of the universe. To truly understand the importance of Stephenson 218 and stars like it, we must step back and look at the larger cosmic processes they influence. Massive stars like Stephenson 218 form in the densest regions of molecular clouds, where gravity causes gas and dust to collapse and condense. These regions are known as stellar nurseries, and it is here that the birth of new stars begins. In these nurseries, the dense gas and dust collapse under their own gravity, eventually forming protostars, young, hot stars that will soon begin the process of nuclear fusion. As these protostars continue to grow, they heat up, and when their cores are hot enough, they start fusing hydrogen into helium, marking the birth of a new star. But the birth of these stars isn't just a simple process. It is the beginning of a cosmic chain reaction that will have far-reaching effects on the galaxy and the universe. The energy produced by a newly formed star has a profound effect on its surroundings. It heats the surrounding gas and dust, creating powerful stellar winds that push material out of the region and help to clear the space around the star. This process, known as feedback, has two main effects. First, it helps to shape the star's environment, preventing further collapse in the surrounding gas and dust. Second, it influences the formation of new stars. In regions where the gas has been cleared away, new stars can form more easily. But the energy released by these stars also contributes to the ongoing evolution of the galaxy. Stars like Stephenson 218, massive and short-lived, are the main drivers of galactic evolution. Massive stars burn through their fuel at an accelerated rate, reaching the end of their lives in a relatively short time. During their brief existence, they emit enormous amounts of energy, and when they die, they explode in a supernova. These supernovae have far-reaching consequences. The explosion of a star like Stephenson 218 creates shock waves that spread out into the surrounding interstellar medium, triggering the formation of new stars and enriching the galaxy with heavy elements. Materials essential for the formation of planets, and possibly life. In addition to influencing star formation, supernovae also play a key role in enriching the universe with heavy elements. As a star like Stephenson 218 fuses elements in its core, it creates heavier elements like carbon, oxygen, and iron. When the star explodes in a supernova, these elements are scattered throughout the galaxy, enriching the interstellar medium. Over time, and this material is incorporated into the formation of new stars and planets. The elements that make up our planets, our bodies, and everything around us were forged in stars like Stephenson 218. But it's not just the stars themselves that shape galaxies. Their death also plays a crucial role. When a massive star explodes in a supernova, it doesn't just scatter elements into space. It creates a shock wave that can trigger the formation of new stars. This process, known as triggered star formation, occurs when the energy from the supernova compresses nearby gas and dust, causing it to collapse and form new stars. The explosion of Stephenson 218 will send shock waves through the surrounding space, potentially triggering the formation of new stars in nearby regions of the galaxy. In the long term, the death of stars like Stephenson 218 helps to drive the ongoing cycle of star formation and galactic evolution. The material produced by supernovae is continually recycled and used to create new stars, planets, and other cosmic objects. Without the death of massive stars, the universe would be a very different place. There would be no heavy elements, no planets, and certainly no life as we know it. Stars like Stephenson 218 are the cosmic engines that drive the evolution of galaxies, ensuring that the universe remains dynamic, constantly changing and growing. As the elements produced by stars like Stephenson 218 spread throughout the galaxy, they are incorporated into the formation of new solar systems. The heavy elements released by a supernova are essential for the formation of planets. Without these elements, there would be no Earth-like planets, no solid surfaces on which life could evolve. In this way, the death of a star like Stephenson 218 is crucial to the formation of planets and ultimately, life. The process of star death and planetary formation is ongoing, and it is what allows for the creation of diverse and complex planetary systems throughout the galaxy. Once a new solar system forms, the elements left behind by stars like Stephenson 218 will give rise to planetary systems that could support life. The formation of rocky planets, like Earth, relies heavily on the elements that are produced in stars and scattered by supernovae. These planets will form from the gas and dust in the surrounding space, using the heavy elements to create solid bodies. Over time, these planets will cool and develop atmospheres, and if the conditions are right, they may become habitable, offering the possibility for life to emerge. For us, as human beings, the death of stars like Stephenson 218 has profound significance. The very atoms that make up our bodies, carbon, oxygen, iron, were likely formed in stars like Stephenson 218 billions of years ago. The iron in our blood, the carbon in our cells, and the oxygen we breathe were all forged in the hearts of dying stars. This process is known as nucleosynthesis, and it is the primary mechanism by which the elements necessary for life are created. In a sense, we are all made of stardust, the remains of stars that lived and died long before the Earth came into existence. As we look to the future, stars like Stephenson 218 will continue to shape the universe. Their explosive deaths will provide the raw materials for the stars and planets of tomorrow. The ongoing cycle of stellar birth and death ensures that the universe remains dynamic and ever-changing. The elements forged in stars like Stephenson 218 will continue to circulate through the galaxy, creating the conditions necessary for the formation of new stars, planets, and possibly life. The death of Stephenson 218 will not be the end of its legacy, but rather a new beginning, a continuation of the cosmic cycle that has shaped the universe since its inception. Stars like Stephenson 218 are not just massive objects in the sky. They are the building blocks of the universe. Their existence and eventual death have shaped the cosmos in profound ways, creating the elements that make up everything around us. Without the death of stars like Stephenson 218, there would be no Earth, no life, and no galaxies as we know them. In this sense, every massive star that burns brightly and dies in a supernova contributes to the ongoing creation of the universe, ensuring that the cosmic cycle of birth, death, and rebirth continues, forever shaping the stars, planets, and galaxies that fill the vast expanse of space. The legacy of discovery, what we've learned and what lies ahead. The discovery of Stephenson 218 was not just the uncovering of a single star. It was a milestone in our understanding of the universe. When astronomers first identified this cosmic giant, hidden behind layers of interstellar dust and located 20,000 light-years away. They were opening a door to a new realm of possibility in stellar science. Stephenson 218, with its immense size and massive energy, challenges everything we know about stars, forcing us to rethink stellar evolution, the limits of star size, and the processes that govern the creation of elements in the universe. But the discovery of such a massive star also highlights an important reality. Our understanding of the universe is far from complete. Stephenson 218 is a remarkable find, but it is not the only giant star out there. The universe is vast, and there are undoubtedly more hidden giants awaiting discovery. Stars that might even exceed the size of Stephenson 218. For astronomers, this means there is still much to learn about the extremes of stellar size and the processes that give birth to such massive stars. The question is, what lies ahead in the future of astronomical discovery? The fact that Stephenson 218 remained hidden for so long is a reminder of the vastness and mystery of space. The star's existence was obscured by thick cosmic dust, and it wasn't until modern infrared technology came into play that scientists were able to peer through the haze and reveal its true nature. Infrared telescopes like the Spitzer Space Telescope and Gaia Space Observatory have revolutionized our ability to observe distant stars, unveiling celestial objects that were previously invisible. This technological breakthrough marks a turning point in our ability to understand the universe, and it offers a tantalizing glimpse of what future discoveries might hold. For example, the Gaia Space Observatory, launched by the European Space Agency, has mapped over 1 billion stars in our galaxy and has been instrumental in measuring the distances, movements, and characteristics of distant stars. Its ability to measure the positions and brightness of stars with incredible precision has allowed astronomers to find and measure stars like Stephenson 218, even those hidden behind thick clouds of interstellar dust. With continued advancements in infrared and space-based technology, astronomers will be able to push the boundaries even further and discover stars and phenomena we can only imagine today. The discovery of Stephenson 218 has raised new questions about the size limits of stars. For decades, scientists believed there were natural upper limits to the size a star could achieve based on the physics of stellar evolution. However, the existence of Stephenson 218 challenges that assumption. The star's massive size has forced astronomers to reconsider their models of star formation and evolution, particularly with regard to how a star like Stephenson 218 could form and maintain such a large size. The discovery suggests that there may be stars out there that are even larger, hidden in regions of space we have yet to explore. This realization also invites a new era of research into the extreme conditions that exist in the cores of supermassive stars. Stephenson 218's size is not just a number. It reflects the underlying physics that allows such a star to grow and remain stable for the relatively short time it has before it reaches the end of its life. What makes a star like Stephenson 218 different from a smaller star? How do these giants manage to continue burning fuel at such a rapid rate? These questions will be key to understanding how such massive stars evolve and what their deaths mean for the future of star systems. Understanding massive stars like Stephenson 218 is crucial for our understanding of the chemical evolution of the universe. These stars are responsible for producing the heavier elements, like iron, carbon, and oxygen, that make up planets and, by extension, life. The death of a star like Stephenson 218 in a supernova explosion will scatter these elements across space, enriching the interstellar medium and contributing to the formation of new stars, planets, and potentially life. The study of red supergiants and supernovae helps us understand the very building blocks of life itself. and provides a link between the life cycles of stars and the formation of habitable planets in the universe. But what makes the discovery of stars like Stephenson 218 so exciting is not just the new knowledge it provides. It also opens the door to future discoveries that will continue to expand our understanding of the cosmos. As technology improves, we will be able to study stars in even greater detail, observing phenomena that were previously impossible to detect. For instance, next-generation telescopes, such as the James Webb Space Telescope, are equipped with advanced infrared capabilities that will allow us to study distant stars in unprecedented detail. These tools will help astronomers see even deeper into space, unveiling the most distant and faint stars, many of which may be far larger than Stephenson 218. This new generation of telescopes will also improve our understanding of the birth and death of stars in galaxies far beyond our own. By studying the formation of massive stars in distant galaxies, we can gain insight into how galaxies evolve over time. Massive stars play a key role in the development of galaxies, influencing their shape, structure, and the creation of new stars and planetary systems. As we continue to explore the farthest reaches of space, the study of stars like Stephenson 218 will allow us to piece together the puzzle of galaxy formation, star evolution, and the creation of the elements that make up the universe. In addition to expanding our knowledge of stellar evolution, the discovery of stars like Stephenson 218 has a broader philosophical significance, and it challenges our perceptions of the universe and forces us to confront the limits of human understanding. When we discover something as extraordinary as Stephenson 218, it reminds us how much we still have to learn about the cosmos. It inspires curiosity and wonder, encouraging the next generation of astronomers, physicists, and explorers to continue their search for knowledge. The universe is vast and full of mysteries, and the discovery of Stephenson 218 is just the beginning of a much larger journey into the unknown. The exploration of these cosmic giants, this also has profound implications for the search for extraterrestrial life. Understanding how massive stars like Stephenson 218 contribute to the formation of planets and the spread of life-essential elements is a critical part of the ongoing search for life beyond Earth. Then, as we study the birth and death of stars, we learn more about the conditions that might support life on other planets. The discovery of Stephenson 218 and similar stars provides valuable insight into the processes that lead to the formation of planetary systems and perhaps even life elsewhere in the universe. Looking ahead, the legacy of Stephenson 218's discovery will continue to shape the course of astronomical research for years to come. As we advance our technology and understanding of the universe, the study of massive stars, supernovae, and the elements they create will remain a cornerstone of astrophysical research. We are still in the early stages of this journey, and the questions raised by stars like Stephenson 218 will continue to inspire future generations of scientists to reach for the stars and expand our knowledge of the universe. The discovery of this cosmic giant is just one chapter in the ongoing story of the universe, and the future holds even greater revelations waiting to be uncovered. The future of stellar discovery. What lies beyond Stephenson 218? The discovery of Stephenson 218 has expanded our understanding of the cosmos, but it has also raised an important question. What else is out there waiting to be discovered? While Stephenson 218 holds the title of the largest known star, its existence challenges us to rethink what we know about the boundaries of stellar size. It suggests that there may be even more massive stars hidden in the depths of space, yet to be uncovered. The discovery of such a colossal star has opened the door to a new era of exploration, one that promises to unveil even greater cosmic giants and answer fundamental questions about the nature of the universe. The key to unlocking these mysteries lies in the continued advancement of astronomical technology. Our ability to observe and measure stars, especially those as distant and massive as Stephenson 218, is limited by the instruments we have at our disposal. But the tools available to astronomers are evolving at an unprecedented rate. And with each new technological breakthrough, our understanding of the universe expands. Future telescopes and space observatories will play a pivotal role in uncovering more of the cosmos' secrets, allowing us to explore even the most hidden and distant regions of space. One of the most significant advancements in the future of stellar discovery is the development of infrared astronomy. Infrared telescopes have revolutionized our ability to see through the dense clouds of gas and dust that block our view of stars like Stephenson 218, revealing the secrets of the universe that would otherwise remain hidden. But as powerful as infrared technology is, there is still much we have yet to see. New infrared observatories, like the James Webb Space Telescope, will allow astronomers to peer even deeper into space, providing a level of detail and clarity that will transform our understanding of distant stars. The James Webb Space Telescope, JWST, which is set to launch in the near future, will have an unprecedented ability to detect infrared light from the most distant stars. With its advanced mirrors and instruments, JWST will be able to observe stars that are so far away that their light has taken billions of years to reach us. It will have the ability to study the formation of stars, the evolution of galaxies, and the birth of planetary systems, all in greater detail than ever before. JWST is expected to discover more massive stars, perhaps even stars that exceed the size of Stephenson 218, and it will provide the data needed to refine our models of stellar evolution. But infrared technology is not the only area where innovation is taking place. Future telescopes will also harness the power of gravitational wave astronomy. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, have already been detected from events such as the collision of black holes. By studying these waves, astronomers will gain insight into the most extreme events in the universe, such as the collapse of massive stars and the formation of black holes. These observations will provide new clues about the final stages of a star's life, including how stars like Stephenson 218 end their journey in explosive supernovae. Beyond infrared and gravitational wave technology, radio astronomy will also play a key role in uncovering the secrets of distant stars. The study of radio waves emitted by distant objects in space will allow scientists to explore the properties of stars, galaxies, and black holes. Radio telescopes like the Square Kilometre Array, SKA, which will be the largest radio telescope ever built, will provide unparalleled insight into the universe's most distant and faint objects. The SKA will be able to detect the faintest signals from stars, providing valuable data on their formation, evolution, and the materials they produce. These advances in technology will not only allow us to discover more stars like Stephenson 218, but will also help us answer the deeper questions that have long eluded us. How do massive stars like Stephenson 218 form in the first place? What role do they play in the larger context of galaxy formation? How do their massive explosions influence the environments around them? And most importantly, what can the study of these stars tell us about the fundamental processes of the universe? In addition to these technological advancements, the future of stellar discovery will also involve the study of stars in distant galaxies. As our telescopes become more powerful, we will be able to study stars that are billions of light years away, giving us a glimpse into the early stages of the universe's evolution. The study of these distant stars will help us understand how galaxies form and evolve, and how the first generation of stars created the heavy elements that make life possible. One of the most exciting areas of future research is the search for stars in the very early universe, the stars that formed shortly after the Big Bang. These population 3 stars, as they are called, are the first generation of stars, and they are believed to have formed from the primordial gas of hydrogen and helium that existed shortly after the Big Bang. These stars would have been incredibly massive and short-lived, and their deaths would have triggered the formation of the heavy elements that we rely on today. By studying the remnants of these stars, astronomers hope to learn more about the early universe and the processes that led to the formation of galaxies, stars, and planets. But even as technology advances and our understanding of the universe deepens, there will always be new mysteries to solve. The universe is vast, and its complexity is beyond our comprehension. The discovery of Stephenson 218 has given us a glimpse into the extreme conditions that govern the lives of the universe's most massive stars. But there is still much more to explore. As we continue to study the cosmos, we will undoubtedly uncover new cosmic giants, each one pushing the limits of what we thought was possible. The discovery of Stephenson 218 has also sparked a broader philosophical question. How do we fit into this grand cosmic story? We are but a tiny speck on the surface of our planet, which itself is just a small part of the solar system, which is merely one star among billions in the Milky Way galaxy. Yet, as we study stars like Stephenson 218, we are reminded of the deep connections between the universe's past, present, and future. The elements forged in the cores of stars like Stephenson 218 are the building blocks of life, and the processes that shape stars are the same processes that shape planets, galaxies, and everything in the cosmos. The story of stars like Stephenson 218 is not just about these individual objects. It's about the larger cycles of creation and destruction that drive the evolution of the universe. The death of a star like Stephenson 218, through the process of supernova explosion and cosmic recycling, ensures that the universe will continue to evolve, creating new stars and planets for billions of years to come. The materials produced by stars like Stephenson 218 will continue to form new solar systems, enriching the universe with the elements necessary for life. The future of stellar discovery is bright, and the journey has only just begun. As we continue to explore the universe, we will not only uncover new stars and galaxies, but we will also learn more about the fundamental processes that govern the cosmos. And as we study these stars, we will gain a deeper understanding of our place in the universe, how we are connected to the stars, and how the elements that make up life on Earth were forged in the hearts of dying giants. A giant's legacy. What Stephenson 218 teaches us about the universe. The discovery of a star as massive and distant as Stephenson 218 serves as a profound reminder of how little we truly understand about the universe. As humanity has gazed up at the stars for millennia, we have learned to see them as distant points of light, part of a vast, unfathomable expanse. Yet, the revelation that a single star can be so vast, so powerful, challenges our perceptions of what's possible in the cosmos. Stephenson 218's discovery forces us to confront the limits of our current knowledge and raises new questions about the nature of stars, their life cycles, and their impact on the universe. In the grand timeline of cosmic evolution, the life cycle of a star like Stephenson 218 is short-lived. While stars like our Sun can live for billions of years, Stephenson 218's life cycle will span only a few million years, a brief moment in the cosmos. But in that brief moment, massive stars like Stephenson 218 exert an immense influence on the surrounding galaxy. From the formation of new stars to the creation of elements that are essential for life itself. Their explosive deaths, in the form of supernovae, send shockwaves through space, enriching the interstellar medium with heavy elements and triggering the formation of new stars and planetary systems. In this way, stars like Stephenson 218 are central players in the cosmic cycle of birth, death, and rebirth. The discovery of Stephenson 218 also highlights the incredible advances in astronomical technology that have allowed us to see deeper into the universe than ever before. Modern telescopes and observatories have revolutionized our ability to observe stars, galaxies, and other distant cosmic objects. Infrared astronomy, in particular, has made it possible to peer through the dense clouds of cosmic dust that obscure our view of distant stars, revealing objects like Stephenson 218 that were once hidden from view. Without the development of infrared technology, the true scale and power of such stars would remain hidden, leaving astronomers to only speculate about their existence. The role of modern space-based telescopes like the Gaia Space Observatory and the James Webb Space Telescope cannot be overstated. These cutting-edge instruments have allowed astronomers to measure the positions, distances, and properties of stars with unprecedented accuracy. In fact, it was the combination of infrared technology and precise measurements from the Gaia Space Observatory that enabled astronomers to determine the true size of Stephenson 218, a star so large that it surpasses all other known stars in terms of volume and luminosity. But what makes these discoveries even more exciting is that they are just the beginning. As new telescopes and space-based observatories come online, the ability to measure and study distant stars will continue to improve, leading to even more groundbreaking discoveries. But what makes Stephenson 218's discovery particularly fascinating is not just its sheer size or its status as the largest known star. Its discovery opens the door to a whole new realm of possibilities in stellar physics. If stars like Stephenson 218 exist, what else could be out there? Could there be even larger stars waiting to be discovered, hidden behind cosmic dust or in far-off galaxies? What does the existence of a star this massive tell us about the physical limits of stellar evolution? And perhaps most importantly, what can the study of such extreme stars teach us about the fundamental nature of the universe itself? The discovery of Stephenson 218 is particularly significant for our understanding of stellar evolution. For decades, astronomers have debated the limits of stellar size, how large a star can become before it collapses under its own weight. Stephenson 218's size forces us to re-examine these limits. It suggests that, in certain circumstances, stars can become much larger than previously thought possible. As we continue to study stars like Stephenson 218, we may uncover new principles of stellar physics that will help us understand the very nature of star formation, life cycles, and death. What happens at the extreme limits of stellar mass and size? How do such massive stars form? And what conditions allow them to reach such enormous proportions? Stephenson 218 also contributes to our understanding of stellar death. When massive stars like Stephenson 218 die, they do not simply fade away. They explode in a violent supernova that releases an unimaginable amount of energy. The supernova of a star like Stephenson 218 is a cataclysmic event that outshines an entire galaxy for a brief moment. But even more profound than the explosion itself is the aftermath. The death of a star like Stephenson 218 creates heavy elements like iron, carbon, and oxygen elements that are essential for the formation of planets and life as we know it. These elements are scattered across the galaxy in the supernova's shockwave, enriching the interstellar medium and providing the building blocks for new stars and planets. In this way, the death of a massive star is not an end, but a new beginning. The next stage in the never-ending cycle of stellar birth, death, and rebirth. The study of supernovae, the violent deaths of massive stars, also has significant implications for our understanding of galaxy evolution. When a star like Stephenson 218 explodes, the shock waves from the supernova can trigger the formation of new stars and planetary systems. These shock waves compress the surrounding gas and dust, causing it to collapse and form new stars. In this way, supernovae play a key role in the evolution of galaxies, driving the cycle of star formation and ensuring that the universe remains dynamic and ever-changing. Without supernovae, the galaxies we see today would not have the same structure, and the elements that make up our planets and life itself would never have been created. But the influence of massive stars like Stephenson 218 extends beyond just star and galaxy formation. These stars also have a profound impact on the environments around them. As red supergiants like Stephenson 218 burn through their fuel, they expel massive amounts of material into space through powerful stellar winds. These winds carry away gas and dust from the star's outer layers, enriching the interstellar medium with the elements produced in the star's core. Over time, this material will be used to form new stars, planets, and other cosmic objects. In this way, even as stars like Stephenson 218 die, they continue to contribute to the formation of new celestial bodies, playing a crucial role in the evolution of the universe. However, the study of stars like Stephenson 218 is not just about understanding the past and present of the universe. It is also about looking to the future. The continued study of massive stars and supernovae will help us understand the future evolution of our own galaxy and solar system. As stars die and new stars are born, they shape the galaxy, determining its size, structure, and the formation of new planetary systems. The study of supernovae also provides insight into the future fate of our Sun. While our Sun is not as massive as stars like Stephenson 218, and it will eventually go through its own death throes, expanding into a red giant before shedding its outer layers and leaving behind a white dwarf. Understanding the life cycles of massive stars like Stephenson 218 can help us predict the eventual fate of our own star, providing us with valuable insights into the future of our solar system. One of the most exciting aspects of the future of stellar discovery is the possibility that we are only scratching the surface of what is out there. The discovery of Stephenson 218 is just the beginning. There are undoubtedly more hidden giants waiting to be uncovered, stars that may surpass Stephenson 218 in size, located in regions of space we have yet to explore. As new telescopes and observatories come online, our ability to detect and measure distant stars will continue to improve. The next generation of astronomers will have the tools to probe deeper into the universe and discover objects that were once beyond our reach. And with each new discovery, we will continue to expand our understanding of the universe's most fundamental processes, from star formation to the creation of life-essential elements. The legacy of Stephenson 218 is not just in the data it has provided, but in the doors it has opened for future research. As we continue to explore the universe and uncover its hidden giants, we will learn more about the nature of stars, their evolution, and their impact on the cosmos. We are only beginning to understand the processes that govern the birth, life, and death of stars. And each discovery brings us closer to understanding the forces that shape the universe as we know it. Stephenson 218's discovery serves as a reminder that the universe is vast, full of mysteries waiting to be uncovered, and that our journey of discovery has only just begun. Searching for new cosmic giants. What's next in stellar discovery? As we stand on the edge of astronomical discovery, it's essential to reflect on the profound implications of what we've learned from Stephenson 218. This star, the largest known star in the observable universe, has opened up a new frontier in our understanding of the cosmos. Yet, the discovery of this cosmic giant is just the beginning. The question now is, how many more stars like Stephenson 218 exist in the universe? Could there be even larger stars hidden in the vast reaches of space, waiting to be uncovered? And if so, what new insights can these discoveries offer about the fundamental workings of the universe? One thing is clear. Stephenson 218 is not the final word on the size of stars. The universe is vast and largely unexplored, and with the rapid advancement of astronomical technologies, the possibility of discovering even more massive stars remains high. The size of a star is not simply a curiosity. It reveals fundamental truths about how stars are born, live, and die. And it forces us to reconsider the physical laws that govern stellar formation and evolution. As we continue to probe deeper into the cosmos, we may find that there are stars even more colossal than Stephenson 218, hidden in distant regions of space or concealed behind dense clouds of gas and dust. The future of stellar discovery lies in cutting-edge technologies that will enable us to observe and measure stars with unprecedented precision. For example, infrared telescopes have already proven their power in unveiling hidden stars by allowing us to see through cosmic dust. Stephenson 218 was first identified thanks to the incredible capabilities of infrared astronomy. But this is just the beginning. Next-generation infrared telescopes, like the James Webb Space Telescope, JWST, will provide a much more detailed view of the universe, allowing us to probe deeper into the cosmos and detect stars that have remained hidden in plain sight. The JWST, set to launch in the near future, will be the most powerful infrared telescope ever built. Its mirrors will be able to detect light from the most distant stars, galaxies, and cosmic objects, and offering insights into stellar properties, star formation, and the evolution of galaxies across billions of years. With the JWST, astronomers will be able to uncover even larger stars, possibly even discovering objects that dwarf Stephenson 218. This telescope will allow us to see stars and systems that formed in the early universe, revealing how the first stars and galaxies came into existence. But infrared telescopes are not the only instruments that will drive the next wave of discovery. Gravitational wave astronomy is also poised to make an enormous impact on our understanding of stellar evolution. Gravitational waves are ripples in space-time caused by massive objects, like black holes and neutron stars, colliding or merging. The detection of these waves has already provided incredible insights into the behavior of dense stellar remnants. But it also opens up a new frontier for understanding the most extreme environments in the universe. The study of gravitational waves could eventually provide clues about the final stages of massive stars, the birth of black holes, and the underlying physics of stellar death. As these new technologies unfold, radio astronomy will also continue to play a crucial role in the search for the universe's largest stars. The Square Kilometre Array, SKA, currently under construction, will be the world's largest radio telescope and will allow astronomers to observe the universe in ways that were previously unimaginable. Radio waves emitted by stars and other cosmic objects contain a wealth of information about their composition, the temperature, and behavior. With instruments like the SKA, astronomers will be able to probe distant regions of space and detect even the faintest signals from stars. This could provide critical insights into the formation and evolution of massive stars, as well as their influence on the surrounding galaxies. Beyond the technological advancements, there are theoretical questions that remain unanswered in stellar research. How do massive stars like Stephenson 218 form? While we know that these stars begin their lives in molecular clouds, where gravity causes gas and dust to collapse into dense cores, the exact mechanisms that lead to the formation of such colossal stars are still unclear. Is it simply a matter of mass accumulation? Or are there other factors that influence how these stars grow to such enormous sizes? What happens in the conditions of such extreme environments that allows stars like Stephenson 218 to burn through their fuel at such an accelerated rate? These are the questions that astronomers will continue to explore in the years to come. Another key question that arises from the study of stars like Stephenson 218 is the nature of stellar instability. Red supergiants like Stephenson 218 are inherently unstable due to the balance of gravitational collapse and nuclear fusion taking place in their cores. As these stars burn through heavier and heavier elements, they experience pulsations and fluctuations that lead to expansion and contraction of their outer layers. What drives these pulsations? How do massive stars maintain their structure under such extreme conditions? And what role do these pulsations play in the eventual death of a star? Understanding these processes is crucial for gaining insight into the behavior of stars at the extremes of their life cycles. The discovery of Stephenson 218 and other massive stars also raises important questions about the physical limits of stellar size. Stephenson 218's sheer volume challenges our understanding of what is possible in stellar physics. Could there be a limit to how large a star can grow based on the physical forces at play? What happens when stars push the boundaries of size and mass? What does the physics behind their formation, stability, and eventual collapse tell us about the forces that govern the universe itself? As we search for more stars like Stephenson 218, astronomers will also be on the lookout for the most distant stars ever observed, objects formed in the early stages of the universe. These early stars, known as population 3 stars, were the first to form after the Big Bang and are thought to have been massive and short-lived. Studying these stars could provide insights into the formation of galaxies, the creation of the first elements, and the processes that led to the evolution of the universe as we know it. Understanding these primordial stars will be crucial for piecing together the early history of the cosmos. The hunt for larger stars and the continued investigation into the limits of stellar size is just one part of a much larger cosmic puzzle. Every new discovery helps piece together the story of the universe's evolution. From the formation of the first stars to the development of galaxies, solar systems, and potentially life itself. As we continue to study stars like Stephenson 218, we will gain insights into the processes that drive the creation and destruction of stars, the formation of planets, and the cycles that sustain the universe. The universe is vast, and we have only scratched the surface of what lies beyond. With each new discovery, we expand our knowledge and push the boundaries of what we know about the cosmos. Stephenson 218's discovery is just one chapter in the ongoing story of the universe's evolution. As we continue to explore the universe, the search for new cosmic giants and the questions they raise will continue to drive the future of astronomy and astrophysics. Each discovery takes us a step closer to understanding the fundamental nature of the universe, our place within it, and the forces that shape the stars, galaxies, and planets around us. As we look to the future, we can be certain of one thing: the journey of discovery will never end. The universe is filled with mysteries waiting to be uncovered, And with each technological advance, we will uncover new cosmic giants, solve long-standing questions, and deepen our understanding of the cosmos. Stephenson 218 may be the largest star we know of today, but it won't be the last. And as we continue to push the boundaries of what we know, we will learn more about the universe's most fundamental processes and the incredible forces that govern the cosmos. Our place in the cosmos. What the discovery of Stephenson 218 means for humanity. The discovery of Stephenson 218, the largest known star in the universe, is not just an achievement for astronomers. It is a milestone in humanity's ongoing quest to understand the cosmos, because it forces us to confront our place in the universe, urging us to ask fundamental questions about the nature of the cosmos, the forces that govern it, and the possibilities of life beyond Earth. As we gaze up at the stars, we are reminded of both our insignificance and our connection to the universe around us. A connection that stretches back billions of years and links us to the very stars we observe. Stephenson 218's discovery invites reflection on the scale and vastness of the universe. This star, located 20,000 light-years away in the Scutum constellation, is a reminder of just how small our corner of the universe really is. 1 light-year is the distance light travels in 1 year, roughly 5.88 trillion miles, 9.46 trillion kilometers. Now imagine a star that is so massive, it would engulf the entire solar system if placed at the center. Stephenson 218 challenges us to understand just how immense the universe is, not only in terms of size, but also in its incomprehensible time scales. The very existence of stars like Stephenson 218 raises a profound question. What is the ultimate purpose of stars and galaxies in the cosmic dance? As massive stars live fast and die young, they contribute to the formation of galaxies, planets, and elements essential for life. The cosmic cycle of birth, evolution, and death of stars is part of an ongoing process that shapes the universe. And by studying stars like Stephenson 218, we get closer to understanding the larger story that links all of creation together. Yet, despite their fleeting lifespans in cosmic terms, stars like Stephenson 218 have an outsized influence on the universe. Their death, in the form of a supernova explosion, produces the elements that make up the planets, stars, and eventually, life itself. In a sense, the death of these stars is a form of creation, as their destruction provides the building blocks for the next generation of stars and planetary systems. Stephenson 218, by dying, will enrich the interstellar medium with the heavy elements that will eventually form new planets, potentially leading to the creation of life. This process, known as cosmic recycling, ensures that the elements formed in stars continue to play a role in shaping the future of the universe. The death of Stephenson 218 will not mark the end of its existence. It will continue to influence the universe for billions of years to come. And this cosmic recycling process is a key part of understanding the evolution of galaxies and the formation of planets. When a star like Stephenson 218 explodes in a supernova, the shock waves from the explosion compress the surrounding gas and dust, creating new star-forming regions. The elements produced by the star are scattered throughout space, enriching the material that will eventually form new stars, planets, and solar systems. Stephenson 218 will contribute to the ongoing creation of new stellar systems long after its death, ensuring that the universe remains dynamic and ever-changing. While the discovery of stars like Stephenson 218 emphasizes the scale and power of the cosmos, it also highlights the fragile nature of life. Our sun, like all stars, will eventually run out of fuel, and its own death will play a role in the creation of new stars and planets. But the death of stars is not just a cosmic event. It has real implications for the future of life on Earth. The study of stars and their life cycles provides insights into the conditions necessary for life to thrive. The elements that make up our bodies, carbon, nitrogen, oxygen, were created in the hearts of dying stars like Stephenson 218. Understanding how these elements are formed, distributed, and incorporated into new star systems is essential for understanding how life could arise elsewhere in the universe. In many ways, the discovery of Stephenson 218 brings us closer to understanding our place in the universe. The very elements that make up our planet and our bodies were forged in stars like it. The atoms in your body, the carbon in your cells, the iron in your blood were created in the heart of stars billions of years ago. We are made of stardust. Every part of us, from the air we breathe to the minerals in the ground, has its origins in the stars that lived and died long before Earth was even formed. This realization underscores the interconnectedness of all life in the universe, binding us to the stars and the processes that govern the cosmos. As we explore the vastness of space, we are also forced to confront the humbling reality that we are just a tiny speck in the grand cosmic picture. The Milky Way galaxy alone contains over 100 billion stars, and there are billions of galaxies in the observable universe. Yet, despite our smallness in the cosmic scale, humanity has managed to reach beyond the confines of our planet, looking to the stars for answers about our origins and our future. The search for life beyond Earth, the study of exoplanets, and the exploration of the cosmos are all part of humanity's quest to understand our place in the universe. The discovery of stars like Stephenson 218 reminds us of the impermanence of all things, even those as vast and seemingly eternal as stars. In the end, every star will die, but it will also give birth to new generations of stars and planets, continuing the cycle of creation and destruction. Stephenson 218's death will mark the end of this particular star, but it will contribute to the ongoing process of stellar evolution. The elements it has created will be passed on to new stars and planets, ensuring that the cycle continues. And just as Stephenson 218's death will create new opportunities for the next generation of stars, it will also help us understand the broader processes that govern the universe. In our search for meaning, the study of stars and galaxies helps us grasp something much larger than ourselves. The fundamental processes of nature, the way the universe evolves, and our small but significant place in it. Stephenson 218's discovery is a reminder that we are part of a much larger story, one that stretches across billions of years and spans the vast reaches of space. By studying the stars, we learn about the very forces that shape the universe, from the birth of galaxies to the formation of planets and the emergence of life. But perhaps the most profound lesson we learn from the study of stars like Stephenson 218 is that we are connected to the universe in ways we are just beginning to understand. The same forces that govern the life and death of stars also influence the evolution of life on Earth. The elements produced in stars are the building blocks of life, and through the death of stars like Stephenson 218, the universe creates the conditions necessary for life to exist. In this way, the death of a star is not just an end. It is a beginning, a continuing cycle that sustains the universe and everything in it. As we continue our exploration of the cosmos, we are reminded that the universe is a dynamic and ever-changing entity, one that is constantly evolving, creating new stars, galaxies, and planetary systems. But more than that, the study of stars like Stephenson 218 reminds us of the preciousness of life on Earth. The elements that make up the planets, the stars, and everything in the universe are part of an ongoing cosmic dance that links us all together. The discovery of Stephenson 218 gives us a glimpse into the grandeur of the universe and invites us to reflect on our place within it. The philosophical implications. What does the discovery of Stephenson 218 mean for humanity? The discovery of Stephenson 218, the largest known star in the observable universe, may seem like an achievement confined to the realm of scientific discovery. But in many ways, it's something far more profound. This discovery has far-reaching implications for the way we think about our place in the cosmos, our understanding of the universe's origins, and the cosmic cycles that shape the universe. In contemplating the discovery of such a colossal and powerful object, we are compelled to ask questions not only about how stars form, evolve, and die, but also about our own existence and the nature of life itself. At the heart of these philosophical questions is the recognition that we, as human beings, are intimately connected to the stars. The very elements that make up our bodies, the air we breathe, and the planets we live on were created in the hearts of stars, just like Stephenson 218. These stars are the factories where the building blocks of life are forged. Elements like carbon, nitrogen, oxygen, and iron, all of which are essential for the existence of life as we know it. The discovery of Stephenson 218, then, is not just the discovery of a single star, and it's a reminder that the entire universe is interconnected in ways we are just beginning to comprehend. The universe as a cosmic cycle. At its core, the life cycle of Stephenson 218 reveals something incredibly humbling about the nature of existence. All stars are born, live, and die in cycles that repeat across the cosmos. The death of one star is not an end, but a transition into something new. A transition that ripples across the universe, influencing the creation of new stars, planets, and even life. This idea of the cosmic cycle, where death begets life, is a powerful metaphor for the way in which the universe evolves. The creation of Stephenson 218, its explosion as a supernova, and the scattering of its elements across space will eventually lead to the formation of new stars and planetary systems, continuing the cycle of cosmic creation. This cycle of birth and death is not unique to stars like Stephenson 218, but it serves as a potent symbol of the impermanence of all things. Every living organism, every star, and every galaxy is subject to this cycle. And yet, in the process of dying, each contributes to the creation of something new. The elements forged in stars like Stephenson 218 will be scattered throughout the universe, enriching the interstellar medium and becoming part of the next generation of stars, planets, and potentially, life. In this sense, the death of Stephenson 218 will give rise to new worlds, new systems, and new opportunities for life to evolve, potentially in ways that we cannot yet imagine. This cosmic cycle offers us a humbling perspective on our own existence. We are part of a much larger, yet ever-evolving system. Just as Stephenson 218's death will pave the way for future generations of stars and planets, our actions and our contributions to the world will have lasting effects that continue long after we are gone. The idea that life is a part of an ongoing cycle of creation and destruction encourages us to think about our own place in this process and how we can contribute to the ongoing evolution of the universe. We are not merely passive observers of the cosmos. We are participants in an ever-changing system. The limits of human knowledge. The discovery of Stephenson 218 also raises important philosophical questions about the limits of human knowledge. How much do we really know about the universe? For centuries, humanity has looked up at the stars with wonder. But our understanding of the cosmos has always been limited by the tools and technologies available to us. The discovery of stars like Stephenson 218 reveals just how much more there is to learn. While we have come a long way in our understanding of stellar evolution, there is still so much we don't know about the universe. Stephenson 218's existence forces us to confront the limitations of our knowledge and challenge assumptions we've held for centuries. If stars like Stephenson 218 exist, what else is out there? How many more hidden giants remain undiscovered in the depths of space? What other surprises does the cosmos hold, waiting to be uncovered by future generations of astronomers and explorers? Each new discovery leads to more questions, and that, in many ways, is the beauty of scientific exploration. Yet the universe is an ever-unfolding mystery, and each new discovery brings us closer to understanding the fundamental laws that govern it. This also brings us to another philosophical consideration: the question of humanity's place in the vastness of the cosmos. Stephenson 218 is just one of billions of stars in the Milky Way galaxy alone, and our galaxy is just one of billions in the observable universe. The sheer scale of the cosmos can feel overwhelming, but it also forces us to reconsider our significance. Are we merely a speck in the vast universe, or do we have a unique role to play in the grand cosmic story? The discovery of stars like Stephenson 218 challenges us to confront the humbling reality that we are but one small part of a much larger universe. The enormity of the cosmos often makes us feel insignificant, but it also forces us to recognize the interconnectedness of all things. We are part of a larger cycle of creation and destruction, a cycle that stretches back billions of years and will continue for billions more. Our existence, no matter how brief in the grand timeline of the universe, is connected to the stars and the cosmic forces that shape our reality. The search for life beyond Earth. Another important philosophical question raised by the discovery of stars like Stephenson 218 is the possibility of life beyond Earth. As we look at the process of star and planet formation, we are reminded of the potential for habitable worlds in other parts of the universe. If life on Earth arose from the elements created in stars like Stephenson 218, then it's possible that life could exist on other planets that were formed from similar cosmic processes. The discovery of exoplanets in recent years has opened up new possibilities for the search for life beyond our planet. But what are the conditions that make a planet truly habitable? Stars like Stephenson 218 play an essential role in the formation of elements necessary for life, and they influence the formation of new solar systems and planetary systems. The death of a star like Stephenson 218 could contribute to the creation of planets in distant regions of space, potentially offering the conditions for life to arise. The discovery of massive stars like it reminds us of the complex processes that make life possible and encourages us to consider whether we are alone in the universe. The ongoing search for extraterrestrial life is inextricably linked to the study of stellar evolution, as we learn more about the types of stars and planets that are capable of supporting life. The study of stars like Stephenson 218 also brings us back to the question of cosmic purpose. What is the purpose of all these stars and galaxies? Is there a larger design to the universe, or are these cosmic processes the result of random events governed by the laws of physics? The search for meaning in the cosmos is as old as humanity itself. From ancient civilizations that look to the stars for guidance to modern astronomers who seek to understand the fundamental forces of nature, humanity's curiosity about the universe is a fundamental part of our identity. The discovery of Stephenson 218, a star that embodies the extremes of stellar physics, forces us to confront some of the deepest questions about existence itself. We are constantly searching for meaning in the universe, Whether it's in the formation of stars, the creation of life, or our own place in the vast expanse of space. The questions raised by stars like Stephenson 218 inspire us to think deeply about our connection to the universe, the origins of life, and our role in the ongoing cosmic story. The impermanence of stars and life. Finally, the life cycle of Stephenson 218 serves as a poignant reminder of the impermanence of all things, both in the universe and in our own lives. Stars like Stephenson 218, which burn brightly and die young, demonstrate the transitory nature of existence. Their death, in the form of a supernova, marks the end of a cosmic journey that began millions of years ago. But even in their death, stars continue to contribute to the creation of new stars and planets, ensuring that the cycle of life continues. In this way, the death of Stephenson 218 is not the end. It is merely a transition to something new. The death of a star like Stephenson 218 also serves as a metaphor for our own mortality. As individuals, we too will one day come to the end of our lives. But like the stars, we are part of a larger cycle. The elements that make us who we are, our bodies, our thoughts, our actions, are part of an ongoing process that stretches back through time and continues to evolve. Even in death, we contribute to the ongoing evolution of the universe. Just as the death of stars contributes to the birth of new stars and planets. Cosmic cycles, the role of star death and rebirth in shaping the universe. The story of Stephenson 218 is not just about a massive star living and dying. It's about the larger cosmic cycles that govern the universe. These cycles, involving the birth, life, death, and rebirth of stars, are the fundamental forces that shape galaxies, solar systems, and even the conditions that make life possible. The death of Stephenson 218, like the deaths of all massive stars, contributes to the ever-repeating process of cosmic renewal, where the death of one generation of stars leads to the birth of another. Understanding these cosmic cycles requires us to step back and look at the grand architecture of the universe. Stars like Stephenson 218 are not isolated objects. They are part of a vast, interconnected system of galaxies and stellar nurseries. The universe is constantly evolving, with stars forming, living, and dying, in a continuous process that shapes the very fabric of space and time. But how do these stars influence the evolution of galaxies? And what role does their death play in the creation of new stars and planets? The stellar nursery, where stars are born. To understand the impact of star death on the universe, we first need to look at how stars are born. The stellar nurseries, also known as molecular clouds, are the birthplace of stars. These vast clouds of gas and dust are scattered throughout galaxies, and within them, the forces of gravity cause material to collapse, triggering the birth of new stars. As the material condenses, it forms dense cores, which eventually heat up and begin the process of nuclear fusion. And these young stars then begin their journey of stellar evolution. The death of stars like Stephenson 218 is the other side of this cycle. As stars evolve and burn through their fuel, they eventually reach the end of their life. In the case of massive stars, this end is marked by a supernova explosion, a cataclysmic event that releases an enormous amount of energy and scatters elements throughout space. These elements, forged in the hearts of stars during their lifetimes, are crucial for the creation of new stars, planets, and even life. In essence, the death of a star like Stephenson 218 becomes a seed for the creation of new stars and planets, allowing the cycle of cosmic creation to continue. The supernova explosion from Stephenson 218 will have a profound impact on its surroundings. As the star explodes, it will produce a shock wave that travels through the surrounding space, compressing nearby gas and dust clouds. This compression can trigger the formation of new stars, a process known as triggered star formation. The energy and material released by Stephenson 2-18's death will enrich the surrounding interstellar medium with heavy elements, which will eventually become part of new stellar nurseries. Over time, these clouds will collapse and form new stars, continuing the cycle of creation that has been ongoing for billions of years. The role of supernovae in galaxies, the death of stars like Stephenson 2-18, doesn't just contribute to star formation. It also plays a critical role in shaping the very structure of galaxies. When massive stars die in supernovae, they not only scatter elements into space, but also release energy that drives the evolution of the galaxy itself. The explosion of a star like Stephenson 2-18 creates shockwaves that spread through the interstellar medium, influencing the distribution of gas and dust throughout the galaxy. This process can affect the formation of new stars and the growth of existing star clusters. In addition, supernovae help regulate the rate of star formation in galaxies. The shock waves produced by supernovae compress gas clouds, triggering the collapse of new material and the formation of new stars. However, the explosion of a supernova can also blow away gas and dust, preventing the material from collapsing and forming new stars. In this way, supernovae are critical players in the balance of star formation within galaxies, ensuring that new stars are born while also controlling the growth of existing stars. This dynamic process is part of the ongoing evolution of galaxies. Stars are born in stellar nurseries, live out their lives, and then die in supernova explosions that redistribute material and regulate the formation of new stars. The birth and death of stars are intimately tied to the structure and evolution of galaxies. And without the death of massive stars, galaxies would not be able to form in the way we see them today. Cosmic recycling, the creation of life-forming elements. Perhaps the most profound aspect of the death of stars like Stephenson 2-18 is the role they play in the creation of the very elements that make life possible. As stars burn through their fuel, they produce elements through nuclear fusion, and these elements are crucial for the formation of planets and, ultimately, life. For example, carbon, oxygen, nitrogen, and iron, elements that are essential for life as we know it, are all created in the cores of stars during their lifetimes. When these stars die, they release these elements into the surrounding space, enriching the interstellar medium with the building blocks of life. This process of cosmic recycling ensures that the universe remains dynamic, with the materials produced by stars being used again and again to create new stars, planets, and life. The death of stars like Stephenson 2-18 provides the raw material for the creation of new planetary systems. As the shock waves from the supernova spread out into space, they trigger the formation of new stars, which are born from the enriched material left behind by their predecessors. These new stars will go on to form new planetary systems, and in turn, those systems will produce the next generation of life-forming elements. The idea that life itself is the result of the death of stars is both humbling and awe-inspiring. We are all made of stardust. The very elements that form our bodies were once forged in the hearts of massive stars like Stephenson 2-18. When these stars die, they scatter those elements across the cosmos, ensuring that life can continue to emerge in new and unexpected places. In this way, the death of a star is not just an end, but a vital part of the ongoing process of cosmic evolution. From stellar death to life, the ultimate legacy of stars like Stephenson 2-18 is that their death fuels the birth of new stars, planets, mochers, and potentially life. The death of a massive star triggers a cascade of events that reshapes the galaxy, contributes to the formation of new solar systems, and replenishes the building blocks of life. The cosmic cycle of star birth, death, and rebirth ensures that the universe remains rich with the elements necessary for life, creating an ongoing process of creation and destruction that has been at the heart of the universe since its very beginning. When we look up at the night sky, we see stars that have been burning for billions of years, some of which are destined to become giants like Stephenson 218. Their lives may be short in cosmic terms, but they have an enormous impact on the universe. The death of these stars leads to the formation of new stars, new planets, and potentially new forms of life, ensuring that the universe continues to evolve and change. In this way, the death of Stephenson 218 is not a tragedy. It is a necessary and vital part of the ongoing cosmic cycle that sustains the universe, the interconnectedness of all things. Perhaps the most profound philosophical implication of studying stars like Stephenson 218 is the realization that everything in the universe is interconnected. The elements that make up our bodies, our planets, and everything around us were once created in the hearts of stars. When these stars die, they scatter these elements across the galaxy, enriching the cosmos and contributing to the formation of new stars, planets, and potentially life. In this way, the death of stars is not just about the end of one life. It is about the continuation of the cosmic cycle that sustains all of creation, and as human beings, we are part of this cycle. The materials that formed us, the planet we live on, and the stars we gaze at were all part of this ongoing process of birth, death, and rebirth. Understanding the life cycles of stars helps us understand our own place in the universe. We are all interconnected, linked by the very elements that were formed in the hearts of stars like Stephenson 218. The study of stars like Stephenson 218 encourages us to look beyond our own existence and consider the vastness of the universe. It challenges us to recognize that we are part of something much larger than ourselves. The cosmic cycle of birth, death, and rebirth is ongoing, and each new generation of stars, planets, and life is a continuation of the cycles that have been shaping the universe for billions of years. The scientific frontier, how the discovery of Stephenson 218 will shape future research. The discovery of Stephenson 218, the largest known star in the observable universe, has ignited a wave of excitement within the scientific community. It is not just a triumph for astronomers. It is a cornerstone that will fuel further research into the nature of stars, the limits of stellar evolution, and the fundamental forces that govern the cosmos. This discovery has revealed new questions and possibilities, prompting scientists to rethink what they know about the processes that drive the universe's most powerful objects. While the discovery of stars like Stephenson 218 is an exciting scientific achievement, it also marks the beginning of a much larger journey into the unknown. The study of stars, particularly the most massive ones like Stephenson 218, holds the key to understanding the fundamental mechanisms of the universe, from the formation of galaxies to the creation of elements that are essential for life. In the case of Stephenson 218, we are dealing with a star that defies the known limits of size, challenging current models of stellar physics. This revelation has profound implications for astrophysics, pushing the boundaries of what we know about star formation, supernova, and the ultimate fate of the most massive stars. The limits of stellar evolution, challenging existing theories. One of the most significant implications of the discovery of Stephenson 218 is that it forces scientists to re-examine the physical limits of stellar evolution. For years, astronomers believed that there was a natural upper limit to how massive a star could be. Stars much larger than the Sun were believed to be rare, with limits on how far they could grow before their internal pressures became unstable. However, Stephenson 218 challenges these assumptions. The star's size, estimated to be over 2,150 times the radius of our Sun, suggests that our understanding of how massive stars form and evolve is incomplete. This discovery has led astrophysicists to ask fundamental questions. What is the true upper limit of stellar mass? How do such massive stars form in the first place? What physical conditions allow a star to grow to such a size without collapsing under its own weight? Stephenson 218 offers scientists the opportunity to test the boundaries of their models of stellar structure and evolution. By studying this star, astronomers can refine existing theories and potentially uncover new physical laws that govern the formation of massive stars. In particular, the discovery of Stephenson 218 raises questions about the role of stellar winds, the continuous outflow of gas and charged particles from a star's surface, in the evolution of massive stars. As stars grow larger, they experience stronger stellar winds, which can carry away mass from the star's outer layers. This process is thought to play a significant role in the evolution of red supergiants like Stephenson 218. However, the sheer size of Stephenson 218 suggests that there might be other factors at play, which could challenge current models of mass loss in massive stars. What causes such a massive star to remain so large despite these winds? On understanding the balance between stellar wind, radiation pressure, and gravity could provide the key to answering this question. Supernovae and the creation of heavy elements. Another crucial aspect of Stephenson 218's discovery lies in its eventual death. A supernova explosion that will release an enormous amount of energy. Supernovae are the cosmic events that shape galaxies and contribute to the creation of the elements necessary for life. When a star like Stephenson 218 explodes, it ejects its outer layers into space, scattering heavy elements such as iron, carbon, oxygen, and gold throughout the surrounding space. These elements then become part of the interstellar medium, where they contribute to the formation of new stars, planets, and potentially life. In the case of Stephenson 218, its supernova explosion will enrich the interstellar medium with the very materials that make up planets and stars. The discovery of such a massive star offers scientists a unique opportunity to study the processes that take place during a supernova explosion. By studying the remnants of Stephenson 218 and other massive stars, astronomers hope to learn more about how heavy elements are created and how these elements are distributed across galaxies. The supernova of Stephenson 218 could provide valuable data on the amount of energy released during such an event and the types of heavy elements that are produced in the aftermath. This is where observational astronomy, using instruments to gather data from light emitted by stars and galaxies, becomes a critical tool. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope will allow astronomers to observe the light emitted by stars in the final stages of their life. These observations can help scientists model the physics of stellar explosions and gain insight into the elements created during a supernova. The study of such phenomena could help scientists understand the origins of the elements that make up the Earth and, by extension, life itself. The search for other hidden giants. The discovery of Stephenson 218 raises another tantalizing question. How many more stars like it are out there, waiting to be uncovered? Stephenson 218 may be the largest star we know of today. But the universe is vast, and there are likely many more cosmic giants hidden in far-off regions of space. With the continued development of infrared astronomy and other advanced observational techniques, scientists will be able to search for and detect other massive stars that may rival or even exceed the size of Stephenson 218. Future missions, such as the James Webb Space Telescope, are expected to uncover more hidden giants, providing further data to help refine our models of stellar evolution and mass limits. What is particularly exciting is that many of these stars may still be in regions of space we have not yet studied. Large portions of the universe remain unexplored, especially in regions obscured by interstellar dust and gas. Infrared telescopes like Webb, which can peer through the cosmic fog, will open up new windows into these previously hidden regions, allowing astronomers to identify even larger stars or previously undiscovered stellar phenomena. As technology advances, so too will our ability to explore distant parts of the universe, uncovering more cosmic giants and unlocking the secrets of their formation, evolution, and eventual death. Astrophysics in the 21st century. Uncovering the mysteries of the universe. The discovery of Stephenson 218 is part of a larger trend of scientific progress in the field of astrophysics. As observational technology advances, so does our ability to study stars and other celestial objects in greater detail. New telescopes, like the James Webb Space Telescope, the Square Kilometre Array, and the Vera C. Rubin Observatory, promise to revolutionize the way we explore the universe. These instruments will allow scientists to study stars, galaxies, black holes, and other objects with unprecedented clarity, answering questions about the fundamental forces at work in the universe. For example, the Webb telescope, once it is fully operational, will give astronomers an unprecedented view of distant stars and galaxies. Its advanced infrared capabilities will allow scientists to peer deeper into space than ever before, uncovering new stars and phenomena that were previously hidden. This will allow scientists to study not just individual stars like Stephenson 218, but entire regions of space, offering new insights into the formation of galaxies and the role of massive stars in shaping the universe. The discoveries enabled by these technologies will shape the course of astrophysics for decades to come. As new data continues to refine our understanding of stellar evolution, black hole formation, galaxy dynamics, and the very fabric of space-time. The legacy of Stephenson 218 will live on in these future discoveries, providing valuable lessons about the extremes of stellar physics and offering clues about the nature of the universe itself. Looking ahead, the future of star research. In the years to come, Stephenson 218's discovery will continue to inspire astronomers to explore the mysteries of the universe. From the study of massive stars and supernovae to the search for new hidden giants, the field of stellar research is poised to make even greater advances. The study of stars will remain central to our understanding of the cosmos. From the birth of stars in stellar nurseries to their explosive deaths and the creation of heavy elements. As technology continues to evolve, so too will our ability to understand the incredible variety of objects that populate the universe. The future of stellar discovery is bright. Stephenson 218 may be the largest known star today, but its discovery is only the beginning of a much larger journey into the unknown. With new technologies and new missions, we will continue to push the boundaries of what we know, uncovering new stars, new phenomena, and new insights into the nature of the universe. Beyond the stars, what the discovery of Stephenson 218 tells us about the nature of the universe. The discovery of Stephenson 218 may be an achievement in astrophysical research, but it raises deeper philosophical and scientific questions that transcend the specific characteristics of a single star. It forces us to reconsider our understanding of the universe's structure, the forces that shape it, and our place within it. The existence of such a massive and distant object challenges the very way we think about stars, galaxies, and the ultimate fate of the cosmos. In contemplating stars like Stephenson 218, we are forced to ask fundamental questions about the limits of the universe, the nature of matter and energy, and the possibilities for life beyond our planet. The universe as a dynamic, ever-changing entity. One of the most profound insights that the discovery of Stephenson 218 offers is the realization that the universe is dynamic, constantly evolving. The life cycle of a star like Stephenson 218, from its formation to its eventual death in a cataclysmic supernova, underscores the continuous process of cosmic change. The birth of new stars, the death of massive ones, and the ongoing formation of planets are part of an endless cycle that shapes the structure of galaxies and the very fabric of space and time. This ongoing evolution of the universe is a reminder that the cosmos is not static, but constantly shifting and transforming. Stephenson 218, like all stars, is part of this cycle of birth, life, and death. The star's size, power, and eventual destruction highlight the forces that govern the creation and destruction of stellar bodies. But these processes are not just about individual stars. They are the drivers of the universe's evolution. The energy released by stars like Stephenson 218, especially during their death as supernovae, is crucial for shaping the interstellar medium and the conditions necessary for future star and planet formation. Through cosmic recycling, the elements created in stars are used again and again to form new celestial bodies, ensuring that the universe remains dynamic and ever-changing. The ongoing evolution of the universe, driven by the life cycles of stars, challenges our understanding of the cosmos. Rather than being a static, unchanging place, the universe is a constantly evolving entity, shaped by the forces of gravity, radiation, and the fusion of elements. The discovery of massive stars like Stephenson 218 reminds us that the cosmos is an active and dynamic system where creation and destruction are inextricably linked. The limits of the universe and stellar growth. The discovery of Stephenson 218 also forces us to reconsider the limits of the universe. Specifically, the limits of stellar growth. For centuries, astronomers have studied stars and theorized about the upper limits of their size. Until the discovery of stars like Stephenson 218, scientists believed that there were physical constraints on how large a star could become. The discovery of this red supergiant, with a size that surpasses all other known stars, challenges these assumptions and raises the possibility that there may be stars out there that exceed even Stephenson 218's size. This brings us to the core question: what determines the size of a star? How do stars form to become as massive as Stephenson 218? The formation of massive stars is not fully understood, and the existence of stars as large as Stephenson 218 suggests that there may be factors in star formation and evolution that we have yet to uncover. As we continue to study stars like Stephenson 218, we may learn more about the physical forces that govern stellar formation and the process that allows stars to grow to such extraordinary sizes. This is a critical question in astrophysics, as it could lead to new insights into the fundamental laws of physics and how they apply to the formation of stars and other cosmic structures. As scientists refine their models of stellar evolution, they may discover that the universe's limits are far more flexible than once believed. The discovery of a star as massive as Stephenson 218 suggests that there are more extraordinary phenomena in the universe waiting to be discovered. The universe is vast, and we have only begun to scratch the surface of what is possible within it. As new technology opens up new frontiers for exploration, we will continue to push the boundaries of our knowledge about stellar formation, mass limits, and the ultimate fate of the largest stars, the creation of elements, and the origins of life. The discovery of stars like Stephenson 218 also highlights the role of stars in the creation of elements essential for life. When massive stars like Stephenson 218 explode in supernovae, they release a vast array of elements into space, including carbon, oxygen, nitrogen, iron, and gold, the very building blocks of life. These elements, created in the cores of stars during their lifetimes, are scattered throughout the galaxy when the star dies, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. The fact that life on Earth is made of elements created in stars is one of the most profound insights in modern science. We are made of stardust. The very atoms that make up our bodies, our planet, and everything we see around us were forged in the hearts of stars long before Earth came into existence. In this sense, the discovery of Stephenson 218 serves as a reminder that life is not an isolated phenomenon, but part of an ongoing cosmic cycle. A cycle in which the death of stars creates the conditions for new stars, planets, and even life to form. This insight is at the heart of the search for extraterrestrial life. If the elements necessary for life are forged in stars like Stephenson 218, then it follows that life could exist elsewhere in the universe, on planets that were formed from the very same elements. And the study of stars and their death throes offers a glimpse into the conditions that make life possible. And this knowledge may one day lead to the discovery of life beyond Earth. The death of stars like Stephenson 218 is a crucial part of the cycle that sustains life in the universe, and it underscores the interconnectedness of all things, from stars to planets to living organisms. Humankind's search for meaning in the universe. The discovery of Stephenson 218 also raises profound philosophical questions about humanity's place in the cosmos. As we look up at the stars, we are reminded of how small and fleeting our existence is compared to the vastness of the universe. Stephenson 218 is but one star in a galaxy of over 100 billion stars, and our galaxy is just one of billions in the observable universe. Yet, despite our smallness in the grand scheme of things, our ability to study and understand the universe reflects a deep connection to the cosmos. We are not just passive observers of the universe. We are part of the cosmic story, and our curiosity and quest for knowledge drive us to explore the stars and understand our place in the vast expanse of space. The discovery of a star as massive and powerful as Stephenson 218 compels us to think about the future of humanity's journey into space. As we continue to search for life beyond Earth and explore the farthest reaches of space, we are reminded of our interconnectedness with the universe. The study of stars like Stephenson 218 not only helps us understand the origins of life, but also deepens our understanding of the fundamental forces that govern the cosmos. By exploring these cosmic giants, we unlock the mysteries of the universe and, in turn, gain insight into our own existence. The search for other universes. While Stephenson 218 represents the largest known star in our universe, the discovery of such massive stars raises the possibility that there may be other, even larger stars in other parts of the cosmos. The existence of such massive objects also hints at the possibility of other universes, potentially with different physical laws or structures. If stars like Stephenson 218 can exist in our universe, could there be other universes out there with stars of unimaginable size? This question pushes the boundaries of what we know about cosmology and forces us to rethink our understanding of the nature of reality itself. The multiverse theory, which suggests that there may be multiple universes beyond our own, is still a topic of much debate in cosmology. If such universes exist, the laws of physics in those realms could be radically different from our own. Could stars in other universes behave differently than those in our own? Could there be stars that are even more massive than Stephenson 218, governed by different physical laws? These are the questions that arise when we confront the enormity of the universe and the mysteries it holds. The quest for knowledge, human curiosity, and the universe. Finally, the discovery of Stephenson 218 serves as a powerful reminder of human curiosity, our insatiable desire to explore the unknown, to seek answers, and to understand the universe. Our quest for knowledge is what drives us to look up at the stars, to ask questions, and to seek meaning in the vastness of space. Each new discovery, like Stephenson 218, brings us closer to understanding the mysteries of the cosmos. But it also reminds us that there is so much more to learn. As long as our curiosity persists, the search for answers will continue, and we will keep exploring the unknown. The legacy of cosmic giants, how stars like Stephenson 218 shape our future. The discovery of Stephenson 218, the largest known star in the observable universe, is not just a remarkable achievement in modern astronomy. It is a pivotal moment in our understanding of the cosmos. Yet, the significance of this discovery extends far beyond the boundaries of astrophysical research. The legacy of Stephenson 218 and stars like it will profoundly influence future generations of astronomers, physicists, and space explorers. As we continue to peel back the layers of the universe, stars like Stephenson 218 will not only help us understand the past and present of cosmic evolution, but also guide the future of space exploration, offering insights that will shape our understanding of everything from the formation of galaxies to the nature of life itself. The role of technology in expanding the frontiers of space. Exploration. One of the most profound impacts of discovering massive stars like Stephenson 218 is the way it highlights the importance of technological advancement in the field of astronomy. The detection of Stephenson 218 was only made possible through the combined efforts of space-based telescopes, infrared observatories, and cutting-edge computational models that allow scientists to make accurate measurements and predictions about distant stars. The tools we use to observe the universe continue to evolve, and each new technological breakthrough opens up a new frontier in space exploration. The James Webb Space Telescope, JWST, which is set to revolutionize the field of astrophysics, will be instrumental in helping us study stars like Stephenson 218. JWST's advanced infrared technology will allow us to peer even deeper into space, observing distant galaxies, stars, and other cosmic phenomena that have remained hidden from view. With JWST and similar advanced instruments, astronomers will be able to study the formation of massive stars, the conditions that allow for their rapid growth, and how these stars influence the environments around them. The technological capabilities of JWST will push the boundaries of our knowledge, enabling us to observe previously unreachable regions of space and providing unprecedented detail on stars like Stephenson 218. In addition to the infrared telescopes and space observatories, advancements in radio astronomy, gravitational wave detection, and computational simulations are providing us with tools to explore new aspects of the universe. The Square Kilometre Array, SKA, for example, will be the largest radio telescope ever built, capable of detecting faint radio signals emitted by distant stars and galaxies. By combining the data from radio observatories with other observational methods, astronomers will gain a more comprehensive understanding of the processes governing stellar formation, supernovae, and other cosmic events. This interconnected web of observational tools and technologies will continue to be the backbone of future astronomical discovery, uncovering the mysteries of star formation. The discovery of a star like Stephenson 218 also deepens our understanding of stellar formation, how massive stars form in the first place. While we know that stars are born in stellar nurseries from clouds of gas and dust, the formation of stars as large as Stephenson 218 is still a mystery. The process that allows a star to grow to such an enormous size and maintain stability for millions of years is not yet fully understood. Is it simply a matter of mass accumulation? Or are there other factors that contribute to the rapid growth of massive stars? What forces govern the formation of supermassive stars like Stephenson 218? These are critical questions that will be explored by future generations of astronomers and astrophysicists. The study of stars like Stephenson 218 opens the door to a deeper exploration of the conditions required for star formation. Understanding the processes that lead to the birth of massive stars is not just important for understanding the stars themselves, but also for unraveling the formation of galaxies and solar systems. Stars are the building blocks of galaxies, and the formation of massive stars like Stephenson 218 plays a central role in shaping the structures of the universe. By investigating the mechanisms that allow stars to grow to such immense sizes, we can gain valuable insight into the larger processes of galaxy formation and cosmic evolution, exploring stellar death and the creation of heavy elements. One of the most fascinating aspects of studying stars like Stephenson 218 is understanding their ultimate fate. The supernova explosion that occurs when a star like Stephenson 218 reaches the end of its life is one of the most dramatic and violent events in the universe. Supernovae are responsible for the creation of heavy elements, such as iron, gold, and uranium, which are scattered across space and eventually become part of new stars, planets, and life. The study of supernovae will continue to be a central focus of astrophysical research in the future. By studying the remnants of stars like Stephenson 218, scientists can gain insights into the chemical composition of the universe, how heavy elements are created, and how these elements are distributed throughout the cosmos. The legacy of stars like Stephenson 218 lies not only in their sheer size, but also in the elements they create, which are necessary for the formation of planets and life. These elements are part of the ongoing process of cosmic recycling, where the death of stars contributes to the formation of new stars, planets, and ultimately, life. Cosmic recycling, the ongoing cycle of creation and destruction. Perhaps the most profound insight that the discovery of Stephenson 218 offers is the cyclic nature of the universe. The ongoing cycle of birth, death, and rebirth that governs the life of stars, planets, and galaxies. The death of a star like Stephenson 218 marks the end of one chapter in the cosmic story, but it is also the beginning of another. The elements produced by the supernova explosion will be scattered across the interstellar medium, enriching the material that will eventually form new stars, planets, and possibly life. In this way, the death of a star is not an end, but a necessary part of an ongoing cycle of cosmic creation and destruction. This cycle of cosmic recycling ensures that the universe remains dynamic, constantly evolving and giving rise to new stars, planets, and life. It is a cycle that has been going on for billions of years and will continue for billions more. Stars like Stephenson 218 play a central role in this cycle, acting as the engines of creation that forge the elements necessary for life. And while their death may seem like a tragic end, it is actually the beginning of a new chapter, where the materials created by the star's explosion are used to form the next generation of stars and planetary systems. The quest for life beyond Earth. Another key aspect of Stephenson 218's legacy is its contribution to our ongoing search for extraterrestrial life. The elements produced in stars like Stephenson 218 are essential for the formation of planets, and life on Earth itself is made up of those same elements. The study of massive stars and their supernovae can provide insights into the formation of habitable planets and the conditions necessary for life to arise. As we look to the stars, the discovery of massive objects like Stephenson 218 reminds us of the interconnectedness of all things. The very elements that allow life to exist on Earth may also exist on other planets in distant star systems. The discovery of exoplanets in the habitable zones of distant stars has sparked a renewed interest in the search for life beyond Earth. If life arose on Earth from the elements created in stars like Stephenson 218, then it follows that life could exist elsewhere in the universe, on planets that were formed from those same elements. As we continue to study stars and planets in other star systems, we may one day discover evidence of extraterrestrial life. Perhaps life that, like ours, was forged in the aftermath of a massive star's death. Looking toward the future, the role of young astronomers and space explorers. The discovery of stars like Stephenson 218 is not just an achievement for today's astronomers. It is a legacy that will inspire future generations of scientists, engineers, and space explorers. As technology continues to evolve, the tools available to study the universe will become even more powerful, allowing us to peer deeper into space and uncover more cosmic giants hidden in distant corners of the cosmos. The next generation of astronomers will continue to build on the discoveries of the past, developing new techniques and models to explore the most extreme objects in the universe. The study of stars like Stephenson 218 is not just for scientists. It is for all of us. It reminds us of our place in the cosmos and encourages us to think about the larger cycles of life, death, and creation that shape the universe. As we continue to explore the universe, the legacy of stars like Stephenson 218 will live on, guiding our quest for knowledge and inspiring the next generation to reach for the stars.